Let me ask you something simple, almost too simple. What happens when you drop something? You hold a spoon out over the kitchen floor, you let go, and it falls. You know it falls. You have known it your whole life. You knew it before you could talk. A baby drops a spoon off the high chair 100 times in an afternoon, and every single time down it goes, and the baby is delighted, because the baby is running an experiment, and the experiment keeps working. So the spoon falls. Fine, but I want you to sit with that a moment, because I think it is one of the strangest things in the whole world, and almost nobody notices, because it is so ordinary. The spoon does not want to fall. Nobody pushes it. There is no string, no wind, no little motor inside it. You just take away the thing that was holding it up, your fingers, and immediately, without any hesitation at all, it heads for the floor. Something reaches out across empty air and pulls it down. You cannot see the something. You cannot smell it or hear it. But it is always there, patiently, under everything, waiting for you to let go. We give that something a name. We call it gravity. And giving it a name makes us feel like we have explained it, but we have not explained anything at all. We have just agreed on what to call the mystery. The name is a little box we put the puzzle in so we can carry it around without thinking about it too hard. So let us not put it in the box just yet. Let us look at the falling itself. Here is a thing I love. Take that spoon and take a heavy iron ball, a big one, the kind you can barely lift, and hold them both out at the same height and let them go together. Which one hits the floor first? Now almost everybody, the first time, feels in their bones that the heavy one should win. It is heavier. It is pulled harder. Surely it comes down faster. And it is a very reasonable thing to feel. It just happens to be wrong. They land together, the little spoon and the great iron ball, side by side all the way down, and they touch the floor at the very same instant. That is a peculiar thing, and it bothered people for a long time, and it should bother you a little too, because it means the pull and the heaviness are arranged in exactly the right proportion to cancel out. The heavy ball is pulled harder, yes, but the heavy ball is also more stubborn. It takes more pull to get it moving, because it has more stuff in it, more of what we call mass, and mass is just a thing's unwillingness to change what it is doing. So the extra pull on the heavy ball is spent exactly on overcoming its extra stubbornness, and what is left over, the actual falling, comes out the same for everybody. The feather would do it too, if only the air would get out of the way and stop cheating. I am telling you this because I want you to feel right at the start that falling is not about weight. Falling is something the world does to everything equally, generously, without playing favorites. A speck of dust and a mountain fall the same. And once you believe that, once it is really in you, you are ready to go on a journey. Because we are going to take this humble, everyday kitchen floor falling, and we are going to follow it somewhere it has no business going. We are going to fall, you and I, not toward a floor and not toward a planet, but toward the strangest solid object anyone has ever been sure is real. And we will do it slowly, one small step at a time, so that by the end you will have arrived somewhere astonishing, and you will hardly remember climbing. But we are not there yet. We are still in the kitchen. So let me add just one layer. When the spoon falls to the floor, why does it stop? It stops because the floor is in the way. The earth is pulling the spoon toward its center, toward the very middle of the whole planet, and the spoon would love to keep going. It would happily fall straight down through the floorboards and the basement and the rock and the hot, deep insides of the world, all the way to the center, if only all that stuff were not solidly in the way. The floor holds it up. The ground pushes back, so the spoon rests, not because the falling stopped wanting to happen, but because it ran into something it could not get through. Now here is a question a child asks and a professor sometimes forgets to. How fast would you have to throw something to make it not come back? Not just up and down, but up and gone, away for good. You throw a ball up, it comes back. You throw it harder, it goes higher, it comes back. Harder still, higher still, back again. Is there a speed, some magic speed, where you throw it up and it simply never returns? where it climbs and climbs and slips away from the Earth entirely and keeps going forever out into the dark? There is. And it has a name too. A good, honest name. We call it the escape velocity. It is the speed of goodbye. For our Earth, that speed is about 7 miles in a single second. Not 7 miles an hour, which is a gentle jog. 7 miles every second. In the time it takes to say the word escape, a thing moving that fast has already crossed 7 miles of sky. That is how hard you have to fling something to get it free of the whole planet, to beat the pull of all that rock and ocean and iron beneath your feet. It is a big number, and it tells you gravity is not really so weak after all. It only feels weak because you spend your whole life leaning against it and never getting away. And notice, please, that the escape speed depends on two things and two things only. It depends on how much stuff is pulling, the mass, and it depends on how close you are to the center of it, the distance. More mass, harder to escape. Closer in, harder to escape. That is the whole recipe. Hold on to those two knobs, mass and closeness, because for the next 3 hours we are going to do nothing but turn them. We are going to keep the recipe exactly the same, this same falling, this same speed of goodbye, and we are just going to make the mass enormous and the closeness terrifying, and we are going to watch what the ordinary laws of the kitchen do when you push them into a place they were never meant to go. Because here is the thing people get wrong. They think that when you go out to the extreme corners of the universe, to the heaviest and the smallest and the most violent things there are, you need new laws, strange laws, laws that have nothing to do with dropping a spoon. And mostly that is not true. Mostly it is the same laws. The very same pull that guides the spoon to your kitchen floor is the pull we are going to follow all the way down to an object where a single teaspoon of the ground would weigh about 1 billion tons. Same law. Same falling. Just turned up and up and up until it stops looking like anything you have ever seen and starts looking like a kind of madness. And the beautiful part, the part I want you to hold on to as you drift off tonight, is that it is not madness. It is arithmetic. It is the spoon, all the way down. So let me set the scene gently, the way you would lay out the pieces of a puzzle on a table before you begin. Imagine you are out there, far out, past the planets, past the comfortable warm sunlight, out in the cold quiet between the stars. And you are falling. There is no rocket. There is no rope back to safety. There is just you, and your slow tumble, feet first if you like, toward a small point of light in the distance. It is not a bright light. It is not a friendly light. It is a hard little blue-white pinprick, and it is not a star, not anymore. It used to be the heart of a star, a great blazing sun many times bigger than our own, and that star died, and this is what it left behind. A cinder, a city-sized cinder with the weight of the sun folded up inside it. You are going to fall toward that. And nothing much seems to be happening at first. That is the trap of it. And that is what makes it such a wonderful thing to think about slowly, in the dark as you go to sleep. At this distance the pull is gentle. It feels, honestly, like almost nothing. You could close your eyes and not even be sure you were moving. But you are moving, and the falling is quietly gathering speed, and the two knobs, the enormous mass and the shrinking distance, are beginning to turn. And everything that is about to happen to you, every strange and violent and gorgeous thing, is already written in that simple fact you have known since you were a baby in a high chair, dropping a spoon and watching, with perfect delight, as something invisible reached up and pulled it down. So let us follow the spoon. Let us follow it much, much further than anyone in that kitchen ever imagined it could go. And let us begin by asking where a thing like this cinder, this impossible little point of light you are falling toward, could possibly have come from in the first place. To find its birthplace, we have to go to a place you would never suspect, not to some exotic corner of the universe, but to the inside of an ordinary star. A big one, mind you. Take a star that came into the world with, 10 to 25 times the mass of our own sun. That is a heavy thing. And a heavy star lives fast and dies young, the way a bonfire piled high burns down quicker than a single candle. All its long life, That star is doing one thing over and over in its deep hot middle. It is squeezing little nuclei together to make bigger ones, and every time it does that, it lets out a puff of energy. That puff of energy pushes outward, and the whole weight of the star, all that gas, all those millions of miles of it, is trying to fall inward. So the star is really a kind of standoff, a gentle, endless argument between the crush of gravity pulling in and the push of the furnace shoving out. And for millions of years, the argument is a draw. The star just sits there, glowing, balanced, like a stone held up by a fountain of water. But here is the quiet trouble. The furnace runs on fuel, and the fuel changes as it burns. First, the star fuses hydrogen into helium. Then, when the hydrogen in the middle runs low, it burns the helium into carbon. Then carbon into heavier things. And heavier, going up the ladder one rung at a time. Each new fuel burns harder and faster than the last. The star is like a man throwing furniture into a stove to stay warm, starting with the newspapers, then the chairs, then the table, then the doors off their hinges, each thing burning quicker than the last, and each thing bought at a steeper price. And every rung up this ladder builds a heavier ash in the center. Until at last, the star arrives at iron. Now iron is the end of the road, and this is the thing you want to hold on to as you drift off, because it is the hinge on which the whole story swings. Iron will not burn. Not the way the others did. Every fuel before it gave off energy when you fused it. But iron is at the bottom of a kind of valley. If you try to fuse iron into something heavier, it does not give you energy. It takes energy away from you. So the moment the star's core turns to iron, the furnace, for the first time in the star's whole life, has nothing left to push with. The fountain of water simply stops, and the stone that was floating on it discovers, all at once, that it is a stone. What happens next happens faster than you can properly imagine. The iron core, which is something like the mass of our whole sun packed into a ball not much bigger than the Earth, has been holding itself up on a very peculiar kind of stiffness. Not the heat of burning, something stranger. It is holding itself up on the sheer unwillingness of electrons to be crowded. There is a rule in nature, a deep one, that says two electrons cannot be squeezed into exactly the same state in the same place. They resist it. And that resistance, that stubborn refusal of electrons to be piled on top of one another, is a pressure all its own. We call it degeneracy pressure. It has nothing to do with temperature. Even stone cold, those crowded electrons push back. For a while, that stubbornness is enough to hold up a whole sun's worth of iron against gravity, but only up to a point. There is a ceiling, a weight above which even that fierce electron stubbornness gives way. A very clever young fellow worked that ceiling out, and it sits at a bit under 1.5 times the mass of the sun. When the iron core grows past that weight, the electrons lose. They simply cannot hold. And the core, having nothing left to lean on, falls. Not slowly. It collapses inward in about the time it takes you to blink, the inner part rushing down at a good fraction of the speed of light, a ball the size of a planet crushing itself down toward the size of a town in less than a second. And now something has to give, down in that unbearable crush, and what gives is matter itself. Think about what an atom really is. It is a tiny hard nucleus, and then, way out at a great distance in atomic terms, a thin haze of electrons, and in between, almost entirely, nothing. Emptiness. A cathedral with a grain of sand at the altar and a few moths near the ceiling, and nothing at all in the vast space between. All the ordinary stuff you have ever touched, the table, your hand, this whole world, is mostly that emptiness, propped open by those electrons, keeping their polite distance from the nucleus. Well, in the collapsing core, gravity finally wins the argument it has been having with the electrons since the beginning of time. It shoves the electrons down, right into the nuclei. And there, an electron and a proton, forced into the same tiny spot, do something remarkable. They merge, they combine, and they become a neutron, and they spit out a little ghostly particle called a neutrino that goes streaming away into the dark. Do you see what has happened? Piece by piece, proton by proton, the star is unmaking its own atoms. It is deleting the empty cathedrals and leaving only the altars, packed now shoulder to shoulder. All that spacious architecture of ordinary matter, gone, folded up, thrown away. What is left is neutrons. Almost nothing but neutrons jammed against one another with no gaps left to close. A whole sun's worth of them, in a ball you could drive across in 20 minutes. And the outer parts of the star, the great bulk of it that was falling in behind the core, comes crashing down onto this new suddenly rigid ball of neutrons, and it bounces. It rebounds off that unyielding surface, helped along by the flood of those little ghost particles pouring out, and the whole outer star is blown off into space in the single most violent event nature knows how to perform, short of two of these things hitting each other. We call it a supernova. For a few weeks it can outshine 100 billion ordinary stars. It can outshine an entire galaxy. A person standing in a field in the year 1054 in China, in the Middle East, looked up and saw a new star appear where there had been none. Bright enough to read by at night, bright enough to see in the daytime, and it stayed for weeks and then faded, and none of them could have dreamed what it truly was. It was a star turning itself inside out. And when the fire and the smoke of that explosion finally cleared away and drifted off across the sky, there was left behind, sitting in the middle of the wreckage, that small, dense cinder, the thing you are falling toward. I love this next part, because it shows you how science really goes, in fits and lucky guesses long before the proof. Two men, back in the year 1933, sat down and thought about all this before anyone had ever seen the faintest trace of such an object. Their names were Walter Baade and Fritz Zwicky. And Zwicky in particular was a character, sharp-tongued and brilliant and not always easy to be around. The two of them put forward an idea so wild it should not have been taken seriously at all. They said, look, when a big star explodes, what if the thing left in the middle is a star made entirely of neutrons? A neutron star. They even guessed it would be tiny and unthinkably dense. And they made this leap only a year or so after the neutron itself had been discovered as a particle. The paint was barely dry on the very idea of a neutron, and here were these two saying, we think you can build a whole star out of them. And then, for more than 30 years, nothing. No proof. The idea sat on a shelf, a curiosity, a piece of theoretical daydreaming that most sensible astronomers filed away under interesting but probably untestable. How on earth would you ever see such a thing? A ball only a dozen miles across, lost in the enormity of space, far too small and far too faint to spot with any telescope pointed at the light of ordinary stars. It seemed like one of those ideas that might be true but could never be caught. The universe, it appeared, was going to keep this particular secret to itself. It did not, of course. The universe let it slip in the most roundabout way through a young woman with a pair of headphones and miles of paper chart and a patience that would change everything. But we will get to her later when you are further down and the falling has taught you what you need to understand her signal. For now, hold on to just this. The thing you are dropping toward was born in the death of something enormous. It is an ash. It is what is left when a great star spends its whole life fighting gravity and finally, inevitably, loses. Every neutron in it was once a proton and an electron in the belly of a normal star, and before that, hydrogen adrift in a cloud in space, and it was all pressed in one terrible second into this. So when I tell you next just how small it is, and just how heavy, I want you to remember that its smallness is not a flaw. Its smallness is the whole point. Its smallness is what a sun looks like after gravity has finished with it. So let us talk about that smallness, gently, the way you would turn a curious stone over in your hand. Take our own sun. You know it is big. It is so big you could pour 1,000,000 Earths into it and still have room to rattle them around. It is a ball of fire wider than 100 Earths laid side by side. Now imagine gravity reaching into that sun, or into a star even heavier, and squeezing. Not squeezing the way you squeeze a sponge where the water runs out the sides. Squeezing the way nothing in your ordinary life has ever squeezed anything. Squeezing until a whole sun's worth of stuff, or near enough, sits inside a ball you could drive across in 20 minutes. Here is the number, and I want you to hold it lightly, the way you would hold a sleeping bird. About 1 4/10 of the mass of our Sun, packed into a sphere roughly 20 kilometers across. That is about 12 miles. That is the size of a city. Not a big city, a middling one. You could stand on one edge of it, if standing were a thing you could survive there, which it is not, and see clear across to the other side the way you might look across a town from a hill. Think about what that means for a moment. Slowly, our Sun, that unimaginable furnace, that thing so large the Earth is a speck beside it, has been folded down to the size of the place where you buy your groceries. And it did not lose any of its weight in the folding. It is all still there, every last bit of it, just closer together than matter has any right to be. I like to try to feel these things in the body, because a number on its own just slides past you in the dark. So let me hand you a spoon. An ordinary teaspoon, the kind you stir sugar with. Now imagine you could dip that spoon down into the surface of this star and lift out one small scoop of its material. Just a spoonful. How much would that spoonful weigh? Back home, here on Earth, about 1 billion tons. Say that to yourself slowly. One spoonful, 1 billion tons. That is not the weight of a mountain. That is more than the weight of a mountain. That is the weight of every car and every truck and every ship, all of them together, balanced on the end of a spoon you could slip into your teacup. You could not lift it. No crane could lift it. If you set it down on the ground, it would not sit there politely. It would go straight through the floor and through the rock beneath the floor, and it would keep going. Because nothing that we build, nothing that Earth is made of, is remotely strong enough to hold 1 billion tons gathered into a single spoonful. And that is only a spoonful of the outside. That is the calm part. Now where does the weight come from? Why is it so absurdly heavy? Because of what it is made of, and how tightly it is stacked. You are made of atoms, and I always find it a wonderful, slightly embarrassing fact that an atom is almost entirely nothing. If you took a single atom and blew it up to the size of a great cathedral, the nucleus in the center, where nearly all the weight sits, would be a grain of salt, hovering somewhere near the altar. All the rest, all that soaring empty space up to the roof, is just the thin whisper of the electrons, and mostly it is simply void. You are built out of cathedrals full of nothing. So is your chair. So is the mountain. So is the sun. A neutron star is what you get when you take away the cathedral and keep only the grains of salt. When gravity squeezed the dying star, it crushed the electrons down into the nuclei, and the protons and the electrons married each other and became neutrons, and those neutrons packed shoulder to shoulder with no roomy empty space between them at all. So the density is not a little more than ordinary matter. It is not 1,000 times more, or 1,000,000 times more. It is something on the order of 300, 400, 500 million billion kilograms in every cubic meter. Written out, it is a number with 17 zeros trailing after it, and there is no point in my saying all those zeros to you in the dark, because the ear cannot hold them. What matters is the feeling. The feeling is this: it is about as dense as the nucleus of an atom itself. The star is not a ball that contains nuclear matter. The star is, near enough, one single colossal nucleus, 20 kilometers wide, held together not by the force that holds ordinary nuclei, but by its own titanic gravity. That is a sun after gravity has finished with it. That is the ash I promised you. Now, you might be lying there thinking a reasonable, drowsy thought. You might be thinking, if gravity is strong enough to crush a whole sun down into a city, what stops it there? Why does it not just keep going? Why does the squeezing not continue until the thing vanishes into a point and becomes one of those holes in space that even light cannot climb out of? It is a very good question, and it is exactly the right question, and the answer is a kind of standoff, a truce between two enormous stubbornnesses. The neutrons, packed that tightly, push back. Not because they are hot, though they are hot. They push back because of a rule in nature, a deep rule about the small world that says you cannot force two of these particles into precisely the same state in the same place. They resist being crowded. Crush them together and they shove outward with a pressure that has nothing to do with temperature at all. We call it degeneracy pressure, which is an ugly name for a beautiful and very obstinate thing. And for a star of the ordinary sort, that outward shove of the crowded neutrons exactly balances the inward crush of gravity, and the two of them settle into an uneasy peace at 20 kilometers across, and there they sit, sometimes for billions of years. But there is a limit to how much even that stubbornness can bear. Pile on more mass, and gravity presses harder, and at some point the neutrons simply cannot hold the line. We have measured some very heavy ones. The heaviest neutron star anyone has weighed carefully carries about 2 1/3 times the mass of the Sun, give or take a little, and it goes by a name that is just a string of letters and numbers, the sort of name astronomers hang on things when they run out of poetry. And the theory says somewhere above that, somewhere around 2 1/5 to nearly 3 times the Sun's mass, there is a ceiling. Cross that ceiling, and the truce breaks. The neutrons give way, gravity wins completely, and the star collapses past the point of no return and becomes a black hole. That boundary has a long name after the 3 men who worked it out, and I will spare you the recitation. Think of it simply as the last stair. Below it you have a neutron star, this impossible dense city of a thing. One step above it you have nothing you can ever see again. So the object you are falling toward is sitting just below that last stair. It is the densest thing in the universe that still has a surface, still has a somewhere for you to land, still has an outside and an inside. A black hole has no surface. It has only an edge, a place past which questions stop being answerable. But a neutron star has a floor, a real, solid, howlingly bright floor, and you are going to reach it, and that fact that there is a floor is what makes falling into a neutron star so much stranger in some ways than falling into a black hole. Because you arrive. Now hold all of this in your mind at once, softly, the way you hold the whole shape of a song. A dead star. A city-sized nucleus. A spoonful heavier than a fleet of ships. A truce between gravity and a crowd of neutrons that refuse to be crowded. And a floor waiting for you at the bottom, brighter and harder than anything that has any business existing. We have not even begun to fall yet. So far, you and I have only been standing at a safe distance, taking the measure of the thing, the way a swimmer stands at the edge of a cold lake and looks at the water before going in. In a little while, I am going to let you step off. And the first surprise, the very first one, is going to be how gentle it feels at the start. Because from far enough away, this monster does not announce itself. From far enough away, its pull is almost polite. It will feel for a while like any ordinary falling, like the falling you have known since you were small and first let go of the edge of the bed. And that politeness is a lie. It is the most dangerous lie in all of physics, and to understand why it is a lie, we have to understand first plainly and patiently what falling really is. Not what it feels like, what it actually is. Because you have been falling your whole life, and I would bet you have never once been told the truth about it. So let me tell you what falling is, and I want you to forget, for a moment, everything you think you know about it. When you let go of something and it drops, the everyday story is that the ground pulls it down. The earth reaches up with some invisible hand and yanks. And that story is fine for building a house or catching a ball. But it is not the truth, and the truth is far stranger and far more beautiful. The truth is that the falling thing is not being pulled toward anything at all. The falling thing is simply going straight. It is doing the most natural, the most lazy, the most honest thing an object can do, which is to keep going the way the shape of space around it tells it to go. And near a heavy thing, the straightest possible path bends. The apple is not tugged toward the earth. The apple is coasting, freely, without a care, along a path that happens to curve into the ground because the earth has quietly bent the space and the time in its neighborhood. Now I know that sounds like a trick of words. Let me make it plainer. Imagine 2 friends who set off walking due north from 2 different points on the equator of a great round world. They start out parallel. Neither one turns. Neither one feels any sideways push. Each of them walks perfectly straight as a person can walk. And yet, As they go north, they drift closer and closer together until at the top of the world they bump shoulders. Something pulled them together, you would swear it, but nothing did. They walked straight the whole time. It was the roundness of the world underneath their feet that carried them into each other. That, and nothing more mysterious than that, is gravity. The falling apple and those two walkers are cousins. Both are going straight through a shape that is curved, and the curving does the rest. So when I say you have been falling your whole life, and no one told you the truth, this is the truth I mean. Every time you have dropped, you were coasting. You were weightless. This is the part that catches people, so let me sit on it a while, because it matters enormously for what happens later at the star. A person falling off a diving board in the second before the water feels no weight. Nothing presses on them. If they closed their eyes, they could not tell, from the feeling in their body, whether they were falling toward a swimming pool or floating in the black between the stars. The falling itself is featureless. It is smooth. It is calm. The rug feels solid under your feet right now, not because gravity is absent, but because the floor is rudely stopping you from falling. The floor pushes up on your soles. That push is the only thing you actually feel. Weight is not the feeling of gravity. Weight is the feeling of being stopped. Take away the floor, and the pressing goes away too. That is why the astronauts float. People think the astronauts float because they have escaped the Earth's gravity, and that is quite wrong. The Earth's pull up there is nearly as strong as it is in your kitchen. They float because they are falling. They and their whole ship are falling together, coasting along a curved path, and since everything falls the same way, nothing pushes on anything else, and so it all drifts as though gravity had politely excused itself. It has not excused itself. It is simply doing its work so evenly that no one on board can feel it doing anything at all. And here is the seed of the whole terror to come, planted very quietly. Everything falls the same way. A feather and a cannonball, a hair and a hammer. If you take the air out of the room, drop together and land together. Galileo saw this, and it is one of the deep and true things about the world. The heavy thing does not fall faster than the light thing. They keep pace, which means that if your whole body is falling, every piece of you falls at the very same rate, your head and your feet and your left hand and your right, all coasting along their own straight paths through the bent space, all in perfect step, and so no part of you tugs on any other part, and you feel nothing. Nothing at all, smooth as sleep. But that is only true, that lovely smoothness, if the falling is even. If every part of you is being told to go the same direction at the same rate. And out in the ordinary world, near the ordinary earth, it very nearly is. Your head is a little farther from the center of the earth than your feet are when you stand, and so the pull on your head is a hair weaker than the pull on your feet. There is a difference. There is always a difference. But it is so absurdly tiny that in your whole life you have never once noticed it, and neither has anyone else, and no instrument in a doctor's office could ever find it. The stretch trying to pull your head off your shoulders as you stand in your kitchen is smaller than the weight of a single grain of salt. You may ignore it. Everyone does. For every purpose that has ever mattered to a human being standing on the earth, falling is perfectly even, perfectly gentle, perfectly smooth. Hold on to that difference, though. That grain of salt. That whisper of a difference between the pull on your head and the pull on your feet. Because that whisper is the thing that is going to kill you at the neutron star. Not the great pull. The great pull, by itself, you would never even feel, for the same reason the astronaut feels nothing. Because if you fall freely, the whole of you falls together. No. It is the difference in the pull, from one end of you to the other, that does the deed. The whisper, and the whole horror of what is coming is contained in one simple idea, which is that as you fall towards something small and monstrously heavy, that whisper does not grow politely. It does not double when the pull doubles. It grows far, far faster than that. So fast that it goes from a grain of salt to a force that could tear a bridge in two over a distance you could walk across in an afternoon. But we are getting ahead of ourselves. I promised patience, and I mean to keep it. Let me back up and ask the plain question that every child asks and no adult answers well. If everything is always falling, and the pull reaches out forever, then how does anything ever get away? How does a thrown ball ever leave your hand? How does a rocket ever climb? The answer is that you can win against the fall, but only by paying upfront in speed. Throw a ball gently and it rises a little, slows, stops, and falls back into your hand. Its straight path curving down into the earth as all straight paths near the earth do. Throw it harder and it goes higher before it turns around. And there is for any world a magic speed. A speed so great that the ball rises and slows, but the world curves away beneath it faster than it can be pulled back, so it never quite turns around. It just keeps climbing forever, coasting out into the dark, free. We call that magic speed the escape velocity. It is not a wall you break through. It is simply the exact price of leaving, paid in one lump sum of speed at the very beginning, and it is a fixed number for any given world. For the Earth, that price is about 7 miles in every second. 11 kilometers a second, near enough. Fire a cannonball that fast, straight up, ignore the nuisance of the air, and it will never come home. That is a great speed by human standards, far faster than any bullet, but it is a speed we can name. A speed our rockets can reach. A speed that belongs to the ordinary world. For the moon, being lighter, the price is cheaper. A little over 1 mile a second, which is why a person could very nearly leap off a small hill on the moon and be in real danger of not coming down for an uncomfortably long while. For the sun, being vast, the price is steep, hundreds of miles a second. So the number tells you something honest about a world. It tells you how tightly that world holds on. The escape velocity is the world's grip, written as a speed. And I want you to keep that idea, the grip written as a speed, in your pocket, because we are going to walk it, step by step, from the friendly 7 miles a second of the Earth up to a number so large it stops being a number about rockets and starts being a number about light itself. That climb is the whole journey. But before we can take even the first step of it, we have to go and find out where such a monstrous grip could ever come from. What kind of object could ever hold on so hard? And to answer that, I have to take you very far from here and very far back to watch an enormous star, a star far greater than our own gentle sun, come to the end of its long life and die. Because the thing you are going to fall into was not built. It was not assembled. It was left behind. It is a corpse. And the manner of its dying is the reason it is the way it is. So come with me and stand at a safe imaginary distance beside one of these giant stars. It is not like our sun at all. Our sun is a comfortable, middle-aged thing, and it will live for billions of years, quietly turning hydrogen into helium in its belly, in no hurry whatsoever. But this star we are visiting was born with the mass of maybe 10 of our suns. Maybe 15. Maybe as many as 25. And here is the first cruel joke that nature plays. You would think that a bigger star, having so much more fuel, would live longer. It is richer, isn't it? It has more to burn. But it is exactly the other way round. The heavy stars are the ones that live fast and die young. A star like this one might blaze through its entire life in only a few million years, which sounds like a long time to you and me, but for a star it is barely a weekend. It burns so hot and so fiercely, squandering its fuel at such a reckless rate, that it races toward its own funeral almost as soon as it is lit. And why does it burn so hard? Because of that same grip we have been talking about, turned inward. A big pile of matter squeezes on itself. All that weight pressing down toward the center makes the middle unbelievably hot and dense, and that heat is what lights the fire. The star is caught, its whole life long, in a kind of standoff. Gravity is forever trying to crush it down to a point, and the fire in its core is forever pushing back out, the way hot gas in an oven wants to expand and push the door open. As long as the fire burns, the star holds its shape. It is a balance, a tug of war where, for a few million years, neither side wins. Pushing in, pulling in, that is gravity. Pushing out, holding the walls, that is the heat of burning. Hold that picture, because the whole death of the star is nothing more than the moment that tug of war is finally, suddenly lost. Now watch what the fire is actually doing, deep down. It starts by fusing hydrogen, the lightest thing there is, into helium, and that gives off energy, and that energy is the outward push. When the hydrogen in the core runs low, the core sags inward a little, gets hotter and starts fusing the helium into carbon. And when the helium runs thin, it sags again, heats again, and burns the carbon into heavier things still. Neon, oxygen, silicon. The star becomes like an onion, if you will forgive me a kitchen picture, with layer inside layer, each shell burning a different fuel, each one hotter and heavier the deeper you go. And each of these stages runs faster than the one before it. The hydrogen burning might last millions of years, but by the time you get down to burning silicon, the whole business is over in about a day. A single day. The star does not know it, but it has one day left to live, and it is spending that day building the very thing that will kill it. Because at the center of all these shells, the ash keeps collecting, and the final ash, the thing that silicon burning leaves behind, is iron. Now, iron is special, and this is the heart of the whole tragedy, so let me say it slowly. Every fusion up to this point has given energy out. You push two light nuclei together, they stick, and they hand you back a little energy for your trouble. That energy is the outward push that has been holding the star up all this time. But iron is the end of the road. Iron is the most tightly bound nucleus there is. If you try to fuse iron into something heavier, it does not give you energy. It takes energy away from you. It costs. So when the core of the star becomes a ball of iron, the fire simply has nothing left to burn that will pay. The furnace, for the first time in the star's whole life, goes quiet. And in that instant, the outward push is gone. Picture it. For millions of years, there has been this perfect standoff. Gravity pulling in, fire pushing out, and now, in less than a heartbeat, one side of the tug of war just lets go of the rope. The iron core, about the size of the Earth but far heavier, has nothing to hold it up anymore. And gravity, which has been patient this whole time, which never once stopped pulling, gets everything it has ever wanted all at once. Now you might ask, and it is a good question, why doesn't the iron just sit there? A rock sits there. A cold iron cannonball sits there and holds its shape and does not collapse. What is holding a cold cannonball up, if not fire? And the answer is one of the most beautiful and strange things in all of physics. What holds up ordinary cold matter, what keeps you from sinking through your chair, is not really the fire of anything. It is a rule about electrons. The electrons in matter refuse, absolutely refuse, to be crammed into the same state as one another. They will push back hard if you try to squeeze them too close, and this pushing has nothing to do with heat or charge. It is a stubbornness written into the deepest laws of the small world. We call it degeneracy pressure, which is an ugly name for a stubborn thing. And in the iron core of the dying star, it is the electrons, standing shoulder to shoulder and refusing to be squeezed, that are making the last stand against gravity. But there is a limit to even that stubbornness. There is a certain weight, worked out by a clever young man named Chandrasekhar, while he was still, I believe, quite young, on a long sea voyage doing his sums. He found that if the core grows heavier than about 1 4/10 times the mass of our sun, the electrons simply cannot win. No matter how stubborn they are, gravity at that weight is stronger than their refusal. And the iron core, sitting there gathering more and more ash from the shell burning above it, creeps right up to that fatal weight. When it crosses the line, the electrons lose, and the collapse that follows is not slow. It is not a sag or a settling. In about the time it takes you to blink, the core of this enormous star, a ball the size of a planet, falls in on itself and shrinks down to something you could drive across in a few minutes. The inner part of it caves inward at speeds that are a good fraction of the speed of light, an entire world falling into a city in less than a second. And where do the electrons go? This is the part I truly want you to sit with, because it is where our neutron star gets its name and its very substance. Gravity squeezes so hard now that it takes the electrons and it takes the protons, the two of them that used to keep a polite distance inside every atom, and it crushes them together into each other. An electron and a proton, forced into the same tiny space, combine and become a neutron. And a little ghost, a nearly weightless particle called a neutrino, comes flying out. This happens not to one atom but to nearly all of them, all at once, throughout the whole collapsing core. The matter you started with, ordinary iron made of protons and electrons and neutrons keeping their arrangements, is unmade. The atoms themselves are undone. The empty space inside every atom, and it is nearly all empty space, remember an atom is mostly nothing, that emptiness is squeezed right out. What is left is neutrons, packed against neutrons, with no gaps, no orbits, no room. The core has become, in effect, one single enormous atomic nucleus the size of a mountain. A mountain, a city, made all of neutrons touching neutrons. And that flood of little neutrinos, those ghostly particles pouring out of the newborn neutron heart, they carry away a staggering amount of energy, and as they blast their way out through the rest of the falling star, they help to tear it apart. The outer layers, which had been falling inward, come screaming back off the hard new neutron core like a wave slapping a seawall, and they are hurled out into space in the brightest explosion the universe knows how to make. A supernova. For a few weeks, this one dying star can shine brighter than all the hundreds of billions of stars in its galaxy put together. It is a light you could see across the whole width of the cosmos. And in the middle of that unimaginable brightness, unnoticed, tiny, the thing that caused it all sits quietly cooling. The corpse. The city of neutrons. The thing that one day, in this long, slow story of ours, you are going to fall into. Two men saw this coming, by the way, long before anyone had ever laid eyes on such an object. Back in 1933, only a year or so after the neutron itself had been discovered in the laboratory, two astronomers named Walter Baade and Fritz Zwicky put the idea forward. They said, in effect, look, when a big star dies in one of these great explosions, what if it leaves behind a star made entirely of neutrons, packed to the density of the atomic nucleus? It was an outrageous suggestion. There was no way then to see such a thing. It was pure reasoning, pure nerve. And for more than 30 years it sat there as a wild idea that most people did not much bother with, until one night a young woman with a radio telescope caught a ticking in the sky that nobody could explain. But that, I promise you, is a story we will come to, and it is worth the wait. For now, hold on to the corpse itself, this ball of pure crushed neutrons, and let us begin, gently, to ask just how much you would have to crush to make one. Take an ordinary thing you know well. A sugar cube, say, the little white kind you might drop into coffee. It sits in your palm, it weighs almost nothing, you could balance a dozen of them on a spoon without noticing. Now I want you to imagine squeezing that sugar cube, not with your hand. No hand could do this. Imagine squeezing it the way gravity squeezes, from every direction at once, patiently, relentlessly, until the empty space inside it is gone, and there is a great deal of empty space inside it. That is the first thing to hold in your mind, and it is a strange thing, because the sugar cube feels perfectly solid. You cannot push your finger through it. Yet almost all of it is nothing at all. Let me tell you how much nothing. An atom, any atom, is mostly a vast emptiness with a tiny hard speck at the center. If I blew up an atom until it was the size of a great cathedral, the nucleus at the middle, the part with all the weight, would be about the size of a grain of salt hovering somewhere near the altar. Everything else, the whole soaring space up to the roof, is just the thin haze of electrons whirring around, holding the shape, keeping other atoms at arm's length. So when you knock on a table and it feels hard, you are not feeling stuff. You are feeling the electric standoffishness of those electron hazes refusing to overlap. The hardness of the world is mostly a kind of politeness between empty spaces. Now, a neutron star is what you get when nature stops being polite. When you crush matter hard enough, the electrons get shoved down into the nuclei, the protons and electrons are pressed together until they turn into neutrons, and all that beautiful cathedral-sized emptiness simply collapses. The grains of salt come together and touch. You are left with the specks alone, packed shoulder to shoulder, with no haze between them. Matter at the density of the nucleus itself, but not one nucleus, no. A whole ball of it, kilometers across. So how heavy would our poor sugar cube be if we could squeeze it to that? Well, let us not use a sugar cube. Let us use something even more homely. A single teaspoon, the amount you might stir into your tea. 1 teaspoon of this crushed neutron material would weigh, here on the surface of the Earth, about 1 billion tonnas. Say that slowly to yourself. 1 billion tonnes sitting in a teaspoon. That is more than every car, every truck, every ship and locomotive humanity has ever built, all of it, gathered into a lump you could rest on your tongue if you were foolish enough, and if it did not instantly plunge through the floor, through the crust of the planet, and keep going. There is no table that could hold it. There is no mountain that could hold it. It would fall through the earth like a stone through fog. That is the density we are dealing with. The numbers the astronomers write down are something like 3, 4, 5, even 7 times 10 to the 17th kilograms in every cubic meter. I do not want you to memorize a figure like that, because a figure like that is just noise to the ear. It does not mean anything to a human being. The teaspoon means something. Hold on to the teaspoon. And now comes the part that I find genuinely difficult to believe, even knowing that it is true. How big is one of these stars? You have all this crushed matter so unimaginably heavy. You might guess it makes some enormous object. It does not. Take about 1 4/10 times the mass of our sun. The sun, remember, is a body so large that you could pour more than 1,000,000 Earths into it. Take all of that, and a bit more, and pack it down to this nuclear density, and what you get is a sphere roughly 20 kilometers across. 20 kilometers. That is about 12 miles. That is the size of a city. You could drive from one side of it to the other in the time it takes to eat lunch. A thing heavier than the sun, and you could fit it comfortably inside the boundaries of a modest town with room to spare for the suburbs. I want you to really sit inside that picture for a moment in the calm dark, because it is the sort of thing the mind slides right off of if you let it. More than the whole sun. The size of a city. If you stood at a distance and somehow could see it lit up, it would look like a little glowing marble hanging in space. And that little marble outweighs a star. Everything that follows in our story, every violent and strange thing that happens as you fall toward it, comes straight out of this one impossible fact. Enormous mass. Tiny size. Nature took the grandest thing she makes, a star, and folded it up into something you could lose in a valley. Now a curious child, and I hope there is a bit of curious child left awake in you, would ask the next question right away. If squeezing makes it smaller and denser, what stops the squeezing? Why doesn't it just keep going, keep collapsing, get smaller and smaller forever? That is exactly the right question, and it is the question that keeps a neutron star from being something even stranger. What holds it up is the neutrons themselves refusing to be packed any tighter. There is a rule in nature, a deep rule about the little particles, that says 2 of them of the same kind simply will not sit in the same state in the same place. They shoulder each other away. Pack them close, and they push back harder and harder, not because of any force you would recognize from everyday life, but because of this stubborn refusal to be identical and in the same spot. We call the push that comes out of it a degeneracy pressure. It is the same kind of stubbornness that, in a weaker form, holds up certain other dead stars. And in a neutron star, it is the neutrons doing the shouldering, and it is very strong, and for a long time it wins. But here is a thing worth staying awake just a little longer for. It does not always win. There is a limit. If you keep adding mass to the neutron star, if you make it heavier and heavier, the crushing weight of its own gravity climbs, and at some point the neutrons, stubborn as they are, cannot push back hard enough. And when they lose, there is nothing left to stop the fall. Nothing at all. The whole thing collapses past the point of no return and becomes a black hole. So a neutron star is a kind of creature living right at the edge of a cliff, held up by the very last thing nature has to offer before the darkness. Where is that cliff edge? We are not perfectly sure, and I will be honest with you about that, because the honest places are the interesting places. The best guess is somewhere between about 2 2/10 and 2 9/10 times the mass of the sun. That is the line, and it has a long name after 3 of the people who worked it out, but you need not carry the name to sleep with you. What matters is that it is a real line, and that real stars press right up against it. The heaviest neutron star anyone has managed to weigh so far spins out in the sky with a designation full of numbers, and it comes in at about 2 35 times the mass of the sun, give or take a little. 2 1/3 suns. Sitting there, near the edge, held up by nothing but the reluctance of neutrons to be crowded. One good push away from vanishing into a hole in space. Think of what that means. There is a narrowest of ranges, a thin band of possible weights, in which a thing can be a neutron star at all. Too light, and the neutrons win too easily, and you never crush hard enough to make one in the first place. Too heavy, and gravity wins, and it disappears. Nature threads this needle over and over all across the galaxy, leaving behind these dense little marbles perched at the boundary of two utterly different fates. And it is toward one of these, sitting quietly at its impossible density, at its city size, at its edge of collapse weight, that I now want you to imagine yourself beginning, very slowly and from very far away, to fall. Because so far I have only told you what the thing is. I have not told you what it does to you. And that, as it turns out, does not begin the way you would expect. It does not begin with violence. From far enough away, this outrageous object, this crushed sun in a valley, greets you with a pull so mild and so ordinary that you would swear there was nothing unusual about it at all. That gentleness is a trap, and it is one of the loveliest lies in all of physics. And understanding exactly how the gentleness turns, step by step, into something no material in the universe can survive, is the whole heart of what we are doing here. So let us step back, out into the cold and the quiet, a long way from the marble, and feel that first deceptively soft tug on the soles of our feet. Picture the space between you and it as a very wide, very still room. There is no floor, there is no ceiling, there is only you, drifting and off in one corner, so small you could hide it behind your thumbnail, that little glowing coin of a star. You are not moving toward it in any hurry. You feel, at first, almost nothing. A whisper against your body, a suggestion, the faintest lean forward, as though someone across the room had quietly asked you to come closer, and you had, without quite deciding to, begun to oblige. If I put a bathroom scale under your feet out here, and if such a thing made any sense in the emptiness, it would read some small and friendly number. You would not be alarmed. You would think, well, this is a big heavy thing, but big heavy things pull gently from far away, and I have all the time in the world. And you would be right about the pull, and completely wrong about the time. Here is the thing that gravity does, the trick it plays, and it is the same trick whether the object is the Earth or the Sun or this crushed little ember we are falling toward. The strength of the pull depends on how far you are from the center, and it depends on it in a particular impatient way. Cut the distance in half, and the pull does not merely double, it goes up by 4. Cut the distance to 1/3, and the pull goes up by 9. It climbs as the square of how much closer you have come. This is the famous inverse square law, and out in the wide still room it feels almost like a piece of bookkeeping, a dry little rule. But watch what it does to a journey. When you are very far away, halving your distance costs you almost nothing in real terms, because you are dividing a tiny pull into a slightly less tiny pull. The lean grows, but so slowly you would never notice. You could fall for a very long time and feel that the situation is under control. The situation is not under control. The situation was never under control. You simply could not feel it yet. Let me give you a number to hold on to, because it tells the whole story of the trap. If you could stand on the surface of this neutron star, if there were any way to survive standing there, the pull you would feel is somewhere between 100 billion and 10 trillion times the pull you feel right now, sitting or lying wherever you are. People who study these things like to quote a round figure of about 200 billion times Earth's gravity. 200 billion. I want you to sit with that number for a moment, calmly, the way you would sit with the sound of rain. On Earth, if you weigh what a grown person weighs, the planet pulls on you with a force you have carried your whole life without complaint. Multiply that by 200 billion. There is no scale that reads that number. There is no floor that would hold you. A single sheet of paper resting on that surface would be pressed down with the weight of a mountain range. And you, drifting in from far away, are on a road that leads, if you let it, straight to that. But here is the gentleness, the lie spelled out plainly. That 200 billion figure is the pull at the surface, 12 miles or so from the center. Out where you began your fall, thousands upon thousands of miles away, the very same law that promises that monstrous surface pull is delivering you a caress. Same star, same mass, same rule of nature. The only thing that has changed is how far your feet are from the middle, and because the pull climbs as the square of your closeness, almost all of the terror is hidden in the last little stretch of the journey. The star hoards its violence. It keeps nearly all of it for the end, tucked into the final miles, and it hands you the beginning of the trip for free, so that you will come. Now, if all the star could do was pull you as a whole, if it could only take you and speed you up and carry you inward faster and faster, that would be dramatic, but in a strange way it would be survivable in the sense that matters to a falling body. Think about what you feel right now as you read or listen. The earth is pulling you with its full strength, and you feel weight, yes, but you do not feel torn. You feel pressed against your chair or against your bed, because the chair or the bed pushes back. Take that support away, step off a high diving board, and for the second or two before the water, you feel nothing at all. You feel weightless. You are in free fall, and in free fall, the pull of gravity, acting on all of you at once, at the same strength, does not tear you or stretch you or hurt you in the slightest. Astronauts orbiting the Earth are falling the whole time, endlessly, and they float about their cabins peeling oranges. Falling, pure falling, all by itself is the most comfortable thing in the world. So if falling is so gentle, if free fall feels like nothing, then where does the horror come from? What is it, exactly, that will destroy you? It is not the pull. It is the difference in the pull. It is the fact that the star cannot pull on all of you at once with exactly the same strength, because the parts of you are not all the same distance from the center. Let me make this very concrete and very slow, because it is the single most important idea in the whole descent, and everything cruel that follows grows out of it. Imagine you are falling feet first toward the star, arms at your sides, stretched out straight along the line of your fall. Your feet are nearest the star. Your head is farthest. Between your feet and your head there is a bit less than 2 meters of you. Now the star pulls on your feet, and it pulls on your head, but your feet are closer to the center than your head is, by that small human distance. And we just said that the pull grows fiercely as you get closer. So the star pulls your feet harder than it pulls your head. Not by much when you are far away. Out in the wide still room, the difference between the pull on your feet and the pull on your head is so absurdly small that no instrument you own could measure it, and you certainly cannot feel it. But it is not zero. It is never zero. And it is a stretching. Your feet are being tugged forward ever so slightly faster than your head. Something, very gently, is trying to pull you the long way, to make you taller. This stretching between the near part and the far part of a falling body is what we call a tidal force, and I want you to notice that it is the same word we use for the ocean tides on Earth, because it is exactly the same thing. The moon pulls harder on the side of the Earth that faces it than on the side that faces away, and that difference, that tiny imbalance in the moon's grip across the width of our planet, lifts the seas up into 2 bulges, one facing the moon and one on the far side, and the earth turns underneath them, and so twice a day the water climbs up the beach and slides back down again. The tide is not the moon pulling the ocean. The tide is the moon pulling one part of the ocean a little harder than another part. It is a difference, not a force by itself. Hold that in your mind, because it changes everything about what is coming. When you fall toward the neutron star, you are the ocean. And the difference in the star's grip from your feet to your head is the tide, and the tide is going to come in. Now here is where I have to be honest with you about how fast this difference grows, because it does not obey the gentle inverse square law that the pull itself obeys. The tidal stretching, the difference between near and far, climbs even faster. It climbs as the cube of your closeness. Cut your distance in half, and the tide does not go up by 4 the way the pull does. It goes up by 8. Cut it to a third, and the tide goes up by 27. 1 over the distance, multiplied by itself, and then multiplied by itself again. That third factor is the whole difference between a story with a happy ending and a story without one. It means that as you fall in, the stretching force pulling your feet away from your head does not merely grow. It runs away from you. It accelerates its own growth. Every mile you gain toward the star, the tide is climbing a steeper and steeper hill, gaining ground on itself, until in the last stretch it is rising so quickly that the caress of one moment becomes the crushing hand of the next before you could draw a breath. We can even write the shape of this down in a small and honest way, and I will say every piece of it in plain words so nothing hides behind a symbol. The stretching force across a falling object of a given length grows in proportion to the mass of the star, and it grows in proportion to how long the object is, so that a tall thing is torn harder than a short one, and it shrinks in proportion to the distance from the center multiplied by itself and by itself once more. That last part, the distance times itself, the cube sitting underneath everything is the part doing the killing. When the distance is large, that cube in the denominator is enormous, and it makes the whole stretching force vanishingly small, and you drift in peace. When the distance shrinks toward the size of the star, that cube collapses toward almost nothing, and dividing by almost nothing throws the stretching force upward toward the sky. The very same equation that whispered to you out in the cold is screaming by the time you near the marble. It did not change its mind, it was always going to scream. You simply had to come close enough to hear it. So let us hold for a moment on the picture of you still falling, still comfortable, still feeling nothing but that faint friendly lean, with the star growing from a coin behind your thumbnail to a coin at arm's length. Everything is fine. Your feet are being pulled a hair harder than your head. But it is a hair, it is nothing, you cannot feel a thing. And meanwhile, underneath the calm, that cube is quietly doing its arithmetic, counting down the miles, sharpening the difference, waiting. The gentleness has not ended, it is simply running out. And the question we come to next, the question that turns this from a pleasant fall into the thing you will not forget, is this. At what distance, exactly, does the tide stop being a whisper across your body and become a force that no rope, no bone, no bar of steel, nothing that has ever been built or grown or forged can hold together? Let me try to answer that with a number, because a number here is worth more than 1,000 adjectives. Somebody once did the honest arithmetic, and I want to walk you through it slowly, the way you would walk through a friend's garden, stopping at each plant. Imagine, instead of your soft and complicated body, a simple rope. A good rope, an honest rope, the kind that could hold a heavy man off the side of a cliff without a second thought. Give it a strength of 10,000 newtons. What does that mean? It means you could hang about a ton of weight off it here on Earth, and it would not snap. That is a serious rope. And now we let this rope fall, hanging straight down, pointed like a plumb line, toward a neutron star that carries a little more than 2 solar masses. Call it 2 1/10 times the mass of the sun. Down it goes. And as it falls, the top of the rope and the bottom of the rope are at slightly different distances from the star, so they are pulled with slightly different strength, and that difference tries to stretch the rope. Far away, that stretch is nothing, a yawn, a rounding error. But remember the arithmetic that cube in the sky is doing. The stretching force grows as 1 divided by the distance cubed. Halve the distance, and the stretch does not double, it goes up by 8. Cut the distance to 1/10, and the stretch grows 1,000-fold. So the rope falls through a whisper, and then a murmur, and then a mutter, and then, quite suddenly, a roar. And the question is only, at what altitude does the roar exceed 10,000 newtons and tear the rope in two? The answer is about 190 kilometers from the center of the star. Now I want you to feel how strange that number is. 190 kilometers. That is a modest drive. That is the distance between 2 cities that share a weather report. And the surface of the star, the actual solid ground of the thing, sits at only about 12 kilometers from the center. So the rope is destroyed at 190 and the surface is at 12. Do the subtraction in your head. The rope has its heart torn out while it is still more than 175 kilometers above the ground. It never arrives. It never touches. It is undone in the empty space of the approach, high up, in what looks from a distance like the safe part of the fall, the part where nothing is supposed to happen yet. And here is the thing I keep turning over, the thing that will not sit still. 10,000 newtons is a very strong rope, but it is not a special rope. Now ask, what about a stronger one? What about a bar of steel? Steel is stronger, so it survives a little longer, it gets a little closer before it fails. But only a little. Because the force is climbing as one over the distance cubed, and a curve that steep does not care very much how strong you are. To buy yourself even a small step closer, you must be enormously, ridiculously stronger. Double your strength and you creep inward by a mere fraction. The wall of tide is nearly vertical. It does not matter whether you are made of rope or steel or diamond or bone. The star draws a line in the sky, a line at roughly that altitude, and it says, on this side you are a thing, and on that side you are pieces, and no material that has ever existed gets to argue with where the line is drawn. You, of course, are not a rope. You are far weaker than a rope, and far more intricate. So your line, the altitude where you personally come apart, is drawn even higher, even farther out, in even emptier space. You would cross it without ceremony. There would be no jolt, no bang, no warning bell. One moment, you are a person falling, feeling that gentle friendly lean in your feet, and a moment later the lean is not gentle, and a moment after that it is not survivable, and there is no clean boundary between those moments that your nerves could ever report to you in time. The whisper becomes the scream inside the space of a breath you do not get to finish. Now I have to stop and correct something, because there is a pretty word that people love to use for this, and the pretty word is a lie, and I do not like teaching lies even by accident. The word is spaghettification. It is a charming word. It paints a picture of you drawn out long and thin and smooth, like a single strand of pasta, like warm taffy pulled between two hands, elegant, tidy, almost graceful. And I understand why the word caught on. It is fun to say, but a woman who thinks hard about these things for a living, an engineer whose whole job is worrying about what happens when objects meet worlds they were not built for, and an astronomer who has spent his life explaining the sky, both of them will tell you the same thing, and they are right. It is not like that. It is not graceful, and it is not smooth. Think about what stretching really is when it is this violent. You are not honey. You are not a noodle of dough that flows. You are a structure, held together in 10,000 different ways, by chemistry, by tissue, by the electrical handshakes between molecules, and every one of those bonds has its own breaking point, and they do not all let go at once in some tidy poetic elongation. They shatter. They rip. They give way in a cascade, the weakest first, then the next, faster and faster as the load that used to be shared gets dumped onto whatever is still holding. It is not drawing taffy. It is more like what happens to a dry twig when you bend it past its limit, except happening to every fiber of you at once, and then happening again to each of the pieces and again to the pieces of the pieces. You are not stretched into a strand, you are torn into a spray, and that spray keeps falling, and the tide keeps sharpening on every fragment, so the fragments tear into smaller fragments all the way down, until what is left is not a body, and not pieces of a body, but a fine mist of matter screaming inward. And that mist has somewhere to go. It has been falling this whole time, and it does not stop falling just because it is no longer you. It rains down onto the star, and it is moving by the time it gets there at a speed that is a serious fraction of the speed of light. Because remember, the escape velocity of this thing is more than half the speed of light, and a falling object arrives carrying every bit of the speed it would need to leave. So this mist, this former you, slams into the ground carrying an appalling amount of energy, energy of motion, energy that has to go somewhere the instant the motion stops. And where energy of motion goes when it is stopped that suddenly is into heat and light and blast. How much? The people who did this arithmetic reached for the biggest yardstick they had, and it was still too small. They said the flash of energy released when even a modest lump of matter strikes the surface of a neutron star would dwarf the entire arsenal of nuclear weapons on our planet. Every bomb ever built, all of them, added together, and this single quiet collision of a single falling body outshines the lot. Not because the body was large. It was not large. You are not large. But it fell from a place where gravity is 200 billion times the gentle tug you feel standing in your kitchen, and it arrived at a speed that gravity like that can give, and speed like that, stopped like that, is a catastrophe of light. So sit for a moment with the shape of what we have found, because we climb to it one small step at a time, and I do not want the height to be lost on you. We began with a thing falling, the most ordinary event there is, an apple off a shelf, a coin off a table. We notice that the pull on your feet is a hair stronger than the pull on your head. We watched that hair, that harmless nothing of a difference, and we followed the one rule that governs it, that it grows as 1 over the distance cubed, and we simply let the distance shrink. We did not add any new force. We did not invent any new physics. We took the same tide that lifts the harbor twice a day and lets the fishing boats out, and we brought it close to a city-sized ball of crushed suns, and the very same gentle idea, unchanged, turned into a wall in the sky that grinds ropes and steel and people into a luminous mist before they ever reach the ground. That is the thing I wanted you to feel. Nothing exotic did this to you. The ordinary did it, taken to an extraordinary place. And yet, even now, even with all of that, we have not touched the ground. The mist has, but we, in our imagination, have not. We have been talking about the space above the star, the approach, the empty air where the tearing happens. We have not yet asked what is actually down there under the point of impact, beneath that flash brighter than every bomb. We have not asked what the ground itself is made of, this ground that is somehow harder than anything we have a word for, this ground that light itself struggles to leave. So let us do that next. Let us set aside the falling for a little while, and let us go quietly, in thought only, and safely, since thought is the one thing the tide cannot shred, down through the surface of this impossible object, and see, layer by layer, what a neutron star is actually built from. Imagine, then, that we are shrunk down to the size of a thought, and we drift onto the surface as gently as a leaf settling on a pond. The very first thing we meet is not solid at all. It is a whisper of gas, an atmosphere, but the strangest atmosphere you could dream of. On Earth, the air above your head reaches up for miles and miles, thinning out slowly so that even the top of a tall mountain still has some air to breathe. Here the whole atmosphere, from the top of it down to the ground it rests on, is thinner than the width of your fingernail. A few millimeters, in some places barely a centimeter. And it is not air, it is plasma, a hot soup of stripped atoms and loose electrons, squeezed into that thin film by a gravity so fierce it will not let the gas puff up the way ours does. Picture the entire sky of a world. Every cloud, every breeze, every layer of weather, all of it flattened into a sheet you could slide under a door. That is the atmosphere of a neutron star. We pass through it in less time than it takes to blink, and we have not even begun. Now we touch the crust. And here I have to be careful with my words, because the word crust sounds ordinary. On Earth, a crust is the skin on a loaf of bread, or the thin, cool rind of rock floating on the hot interior. This crust is nothing like that. It is a solid, and it is made, near the top, of iron. Iron 56, the same iron that sits in your blood and in a nail and in the red rust on an old gate. But the atoms here are not arranged the lazy way they are in a nail. Gravity has stacked them into a rigid crystal, a lattice, each iron nucleus sitting at the corner of a tiny cube, and another one right in the center of that cube, over and over, packed so tight and held so hard that the whole thing behaves like a single crystal the size of a city. I told you earlier the crust is thought to be something like 10 billion times stronger than steel. Sit with that number for a moment, quietly, the way you would sit with a large dark thing at the edge of a field. Steel is already the stuff we build bridges from, the stuff that holds up whole buildings without bending. And this is 10,000 million times more unyielding than that. If you could somehow stand on it and strike it with a hammer, the hammer would learn a hard lesson, and the crust would not so much as remember the blow. Why is it so strong? It comes back to the same thing, always the same thing on this journey. The crushing. On Earth, iron atoms are held together by their outer electrons, which are soft and springy, and that softness is what lets metal bend and dent and scratch. Down here, the electrons have been squeezed off the atoms and set loose, running free through the whole lattice like water flooding between stones. And the bare nuclei are packed so densely and pressed so hard against one another that there is simply nowhere for them to go. There is no give. There is no room to slip. A crystal with no room to slip is a crystal that cannot bend, and a thing that cannot bend, when you make it big enough and dense enough, becomes stronger than anything in our ordinary experience. Let us keep going down slowly, because there is no hurry here and every layer is a small marvel. As we sink into the crust, the pressure climbs and something begins to happen to the iron itself. The nuclei are being squeezed so hard that they start to take on extra neutrons, growing heavy and swollen, bloating far past the neat, comfortable nuclei we know at the surface of the Earth. They become greedy, hoarding neutrons the way a sponge hoards water when you hold it under a running tap. And then, at a certain depth, at a certain pressure, something gives way that has no equal anywhere in your daily life. The nuclei can hold no more. The neutrons begin to leak out of them entirely, to drip out and pool in the spaces between. Free neutrons wandering loose through the lattice, no longer bound to any particular nucleus at all. The people who study these things call it the neutron drip, and I have always thought that is a lovely, homely name for such a strange event, as if the star were a ceiling with a slow leak, drops gathering and falling somewhere in the dark. This is the inner crust, and it is a peculiar double thing, part solid crystal, part loose river of neutrons flowing through the crystal, both at once. And the neutrons that drip out do something no ordinary liquid does. They become a superfluid. Now I want to tell you what that word means, because it is one of the quietest, most beautiful facts in all of physics, and it is worth a moment of wonder before we sink any deeper. When you stir the cream into your coffee, the liquid resists you a little. It has friction inside itself. Layers of it rub against each other, and if you stop stirring, the swirl slows and dies away, because that inner rubbing steals the motion and turns it into heat. That inner rubbing is called viscosity, and every ordinary liquid has it. Honey has a lot, water has a little, but a superfluid has none. None at all. Set it swirling and it will swirl forever, with no rubbing, no slowing, no forgetting. Pour it and it climbs the walls of its own container and creeps over the rim. It has in a certain sense no internal friction whatsoever. And here, deep inside the crust of a dead star, there is an entire ocean of neutrons behaving exactly this way, a frictionless sea, swirling in eddies that may have been turning quietly since before the first fish crawled onto land on Earth. We go on. Below the inner crust, the last of the crystal gives out. There are no more nuclei sitting in their neat little cubes, there is no more lattice, there is only the sea. This is the outer core, and it is almost entirely neutrons, a vast degenerate ocean of them, superfluid, pressed together at a density that beggars every word we have, with just a faint scattering of protons and electrons mixed through, a few in every 100, like a pinch of salt lost in an ocean. When I say degenerate, I do not mean anything shameful. It is a technical word, and what it means is that these particles are packed as tightly as the laws of the quantum world will physically permit. There is a rule, a deep rule, that says two of these particles can never occupy exactly the same state, can never be crammed into precisely the same condition of place and motion. It is a kind of standoffishness written into the fabric of matter. And it is this rule, this refusal of one neutron to be where another neutron already is, that holds the whole star up. That is the thing pushing back against all that gravity. Not the strength of any material, not any force we would recognize from bridges or ropes or stone. It is a stubborn quantum unwillingness of neutrons to be squeezed into the same space, and it is the only thing standing between this star and total collapse into a black hole. Think about how thin a thread that is to hang a star upon. All that mass, more than the mass of our own sun, more than 1,000,000 Earths, all of it bearing down toward the center, and what holds the line is a rule about how you cannot put two neutrons in the same place. Add just a little more mass, push past that limit I mentioned, somewhere above twice the mass of the sun, and even that rule is not enough. The neutrons lose. Gravity wins, and the star falls the rest of the way into darkness. But so long as it stays below that edge, this quiet, invisible quantum refusal holds up a city-sized ocean of superfluid neutrons against a weight that would flatten a mountain range into a film thinner than paper. We are very deep now. The pressure has climbed past anything the human mind was built to picture, and we are approaching the center, the heart of the thing, the inner core. And here I must stop and be honest with you, because honesty is the only thing worth offering when you reach the edge of what anyone actually knows. We do not know what is down here. We truly do not. Here the matter is squeezed to 10, perhaps 15 times the density of an ordinary atomic nucleus, which is already the densest ordinary stuff there is. And nobody has ever made such matter in a laboratory, and nobody has ever seen it, and our equations begin to fray and disagree with one another the way tired travelers argue about the road. Some who study it suspect that down here the neutrons themselves may finally break open. A neutron, you see, is not truly one solid ball. It is made of smaller things, 3 little pieces we call quarks. And in all the ordinary world, those quarks are locked away inside their neutron, never to be seen alone. But at these pressures, perhaps, just perhaps, even that prison fails, and the quarks spill out and mingle freely, a soup of naked quarks that exists nowhere else in the universe that we know of. Perhaps. Or perhaps it is something stranger still, something we have not yet been clever enough to imagine. We have theories. We have careful, beautiful guesses, but we have never touched it, and we cannot see it, buried as it is beneath all those layers, beneath the ocean and the drip and the crystal and the thin flat sky. It is one of the last truly hidden places, sealed away by its own impossible gravity. And I find there is a strange comfort in that, in knowing that even now, even after everything we have figured out, there is still a room at the center of the dead star with the door shut and a light on under it, and nobody has yet been inside. Let me back away from that closed door for a while, because there is something we have quietly ignored while we were falling. All this time I have been talking as though the star was sitting still, patient, waiting for us to arrive. But it is not sitting still. Almost none of them are. The thing you would be falling into is spinning, and it is spinning in a way that has no honest comparison in your daily life. Think for a moment about a figure skater. She spreads her arms wide and turns slowly, and then she pulls her arms in against her body, and suddenly she whirls faster. So fast the crowd gasps. Nothing pushed her. She simply gathered her spread out self into a smaller space, and the spinning had to speed up to keep the books balanced. That is a real law of nature, and nature never forgets it. Now take a whole star, a thing wider than the distance from here to the moon and back many times over, turning lazily once every few weeks. Crush it down into a ball the size of a city. The spinning has nowhere to go but up and up and up. What was a sleepy monthly turn becomes many turns every single second. Let me give you the champion. There is a pulsar with a name that is just a string of numbers, and it turns 716 times, and a little more every second. Say that slowly to yourself, 716 full rotations each and every second. A blade of a kitchen blender, a good angry one, might manage a few hundred turns a second and scream while it does it. This is a ball the size of a city, heavier than our sun, turning faster than that blender, and doing it in perfect silence in the dark. It was pinned down by a young astronomer named Jason Hessels, working at McGill University, and confirmed in the first days of January in the year 2005. It sits in a crowded knot of stars called Terzan 5, somewhere around 20,000 light years from where you are lying right now. And here is the piece that ought to make you sit up, except that you are trying to fall asleep, so let it wash over you gently instead. If you stood at the equator of that star, on the widest part of the belly where the spinning is fastest, the ground beneath your feet would be sweeping along at nearly 1/4 of the speed of light. The surface of a solid object moving at a fair fraction of the fastest speed there is. Not a beam of light. Not a spray of particles. The actual crust, the floor, the physical ground, racing around so quickly that in the time it takes you to blink it, has carried a point on the equator most of the way around the whole star. Now, not all of them are so frantic. The famous one, the Crab pulsar, the glowing heart left behind by a star that people on Earth watched explode in the year 1054, turns a much gentler 30 times a second. Only 30. I say only, and then I catch myself, because 30 turns a second is still faster than any wheel or engine you have ever stood next to. It is just that once you have met the 700-turn monster, the 30-turn one feels almost restful, almost like something you could get used to. That is the trouble with these objects. They keep resetting what your mind is willing to call normal. So picture the fall again, now with the spin included. You are not dropping toward a still target. You are dropping toward a whirling one, and everything near it is dragged along in the whirl. The magnetic field is dragged. The thin wisps of gas above the surface are dragged. Beams of radio waves come sweeping around like the light from a lighthouse once every turn, flick, 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 hundreds of times a second, a rhythm so exact you could set a clock by it, and the clock would keep better time than almost anything human hands have ever built. These little dead cities are among the most reliable clocks in the entire universe. A thing that used to be a star, ticking away in the dark with more precision than a jeweler's finest work. And I have not even told you about the magnet yet. Let me tell you about the magnet, because it is the next layer, and it is a strange one. You have held a magnet. You have felt that soft, invisible push when you bring two of them close and they refuse to touch, or that eager tug when you turn one around and they leap together. That everyday magnet in your hand, the one that holds a note to the icebox, has a certain strength, and we can measure it, and it is modest. The Earth itself is a magnet, a big weak one, strong enough to nudge a compass needle and no more. Now a neutron star. An ordinary one, nothing special, just a run-of-the-mill neutron star, carries a magnetic field something like 100 million to a trillion times stronger than the little field of our whole planet. Not the field of your icebox magnet, the field of the entire Earth, multiplied by numbers I can barely make my mouth say. But even that is not the top of the ladder. There is a rare and furious kind of neutron star that we call a magnetar, and the magnetar makes the ordinary neutron star look like a compass needle in turn. A magnetar's field can reach something on the order of a quadrillion times the strength of Earth's. A quadrillion. A one with 15 noughts trailing behind it. I want to give you a feeling for what a field like that would do, and the trouble is that it would do things so violent that the usual pictures fail. Long before you reach such a star, long before the tides had finished their shredding, the magnetic field alone would be pulling on the very atoms of you. A magnetic field of that strength does not gently arrange things. It squeezes atoms out of their comfortable round shapes and stretches them into thin pencils, aligned along the field. Like a field of wheat all bent flat by the same impossible wind. Chemistry as you know it, the whole friendly business of atoms holding hands to make water and salt and skin, simply stops working, because the shapes the atoms are forced into are not shapes that can hold hands anymore. You would be unmade not by a blade and not by a fire, but by magnetism, quietly, at a distance, before you had even arrived. I keep saying before you arrive. Have you noticed that? Every single one of these effects, the tides, the impact, the light bending back, the magnet, the spin, every one of them reaches out and does its work to you at a distance, long before your feet would ever touch that crust. That is really the deep lesson hiding under all the fireworks. On Earth, things happen when you touch them. You fall, and then you land, and the landing is the event. Out there, near one of these dead stars, there is no clean moment of landing, because the star's influence is so enormous that the reaching out is the whole story, and the touching, if it ever happens, is just a formality performed on something that stopped being you a long way up. Let me slow down here and ask a question I have been dancing around. How on earth did anyone ever find out any of this? You cannot fly there. You cannot drop a probe in and get it back. Nobody has ever seen the crust, let alone the ocean or the sealed room at the center. And yet I have been telling you the spin rates to the decimal, and the strength of the magnet, and the temperature of the glow. Where does the nerve to say such things come from? It comes, as so many things do, from somebody noticing a small stubborn thing that would not go away. In the autumn of 1967, a young woman named Jocelyn Bell was a student, and she was working with a radio telescope, a great homely field of wires and poles she had helped to string up with her own hands. She was watching the sky in radio waves, waves your eyes cannot see, and reading the results off long rolls of paper covered in a wandering inked line. And on the 28th of November in that year, she found a little bit of scruff on the paper, a tiny hiccup in the line. Most people would have brushed it off. A loose wire, a passing car, some bit of human noise leaking in. But she looked closer, and the scruff came back, and when she pinned it down, she found it was pulsing, ticking, with a beat so regular, once every 1 1/3 seconds or so, that it hardly seemed like it could be nature at all. That is the thing that stopped everyone cold. Nature is usually a little sloppy. Nature drifts and wanders. But this was clockwork, so clean, so exact, that for a little while, only half joking and half serious, they wrote on the record the letters LGM, Little Green Men. Because who else keeps such perfect time? Maybe, just maybe, somebody was sending a signal. It was not somebody. It was a neutron star, turning, sweeping its beam past the Earth once each rotation, a lighthouse nobody had known was there. But I love that they let themselves wonder. I love that for a few weeks the grown-up scientists allowed the thought that they might have heard another mind knocking. That is the right spirit. You should always be willing to be wrong in the most interesting possible direction as long as you keep checking. And notice what had happened. Two men, Walter Baade and Fritz Zwicky, had dreamed these stars up on paper back in 1933, more than 30 years earlier. They had said out loud, in effect, that when a big star dies it might crush itself into a ball of neutrons. And people mostly filed it away as an interesting bit of arithmetic and forgot about it. It took a student and a hand-built field of wires and a bit of scruff on a paper roll to turn that old guess into a real thing in the real sky. Think for a moment about what kind of nerve that took. Not the nerve to build the wires, though that was real work, and not the nerve to sit with the paper rolls hour after hour, though that was tedious beyond most people's patience. I mean the nerve to look at a little smudge of scruff, a thing most people would have wiped away as a fault in the machine, and to say, "No, wait, let me look at that again." That is where the whole business lives. The universe does not shout its secrets. It murmurs them, and it murmurs them right in the middle of the noise, so that 99 times out of 100 you would be perfectly reasonable to ignore the murmur. The trick is not to be clever enough to explain the smudge. The trick is to be stubborn enough to keep asking about it after everyone, including the sensible part of your own mind, has told you to move along. And once they knew what they were listening to, everything changed. Because now they could ask the murmur questions. "How fast are you turning?" they asked. And this first one answered, "Once every 1.3373 seconds, steady as anything a human being had ever measured." That is the ticking of a whole dead sun. An object heavier than our own star, spinning around and around and around, its beam brushing past us like the sweep of a lamp in a lighthouse on a coast we cannot see. Some of these things turn slowly, if you can call a full turn every couple of seconds slow. Others do something that I still find hard to hold in my head without a little dizziness. Let me go back to that thing you fell into, the one turning underneath you as you came down. I told you earlier it was spinning. I did not tell you how badly. There is one of these, and it carries a name that is just a string of numbers. PSRJ 1748 minus 2446 AD, and I am sorry for the name, the sky does not hand out pretty ones. A young fellow named Jason Hessels, working out of McGill University, pinned it down, and they confirmed it on the 8th of January 1990. No, I will keep to what I can vouch for. They confirmed it in the winter of 2005. This star turns 716 times every second. Say that slowly to yourself. Not 716 times a day, or an hour, or a minute. 716 full rotations in the time it takes you to say the word rotation. A ball the size of a city, heavier than the sun, and it goes around more than 700 times while a single second of your life goes by. Now what does that mean for the stuff on the outside of it? Picture the equator, the fat middle of the ball, the part farthest from the axis. That surface is not strolling. It is not even sprinting. It is moving at very nearly a quarter of the speed of light. Roughly 70,000 kilometers in a single second, which is to say, in one tick of a clock, that piece of crust has traveled a distance you could not cross in an ordinary lifetime of walking. And it holds together. That is the astonishing part. Anything we could build, anything you have ever touched, spun even a tiny fraction that fast, would have flown apart into a spray of glowing fragments long before. But the gravity we have been talking about all this while, that same monstrous grip that would have shredded you on the way in, that grip is precisely what keeps this thing from tearing itself to ribbons as it whirls. The very thing that would kill you is the thing holding the star together. Gravity, pulling in hard enough to fight against a quarter light speed spin. Hold those two facts side by side and you begin to feel the scale of the pressures inside. And compare that maniac to a gentler cousin, the one sitting at the heart of the crab. That one is the leftover core of a star that blew itself apart, a light that arrived at the Earth long ago in the 11th century. Bright enough that people wrote it down without any idea what they were seeing. That collapsed heart is still there, about 20 kilometers across like the others, and it turns almost 30 times a second. 30 times a second we would already call insane for anything the size of a city. Next to the 700-ton monster, it looks positively lazy, an old grandfather rocking slowly on the porch. That is the range these things come in. From 30 turns a second, which is madness, all the way up to 700 and more, which is madness raised to a power I do not have a good word for. But the spin, wild as it is not the strangest coat the thing is wearing. There is something else wrapped around a neutron star, something invisible, and it is arguably the most extreme condition anywhere in the whole known universe. I mean the magnetic field. Now everybody has felt a magnet. You have stuck one to the door of an icebox, you have watched it grab a paperclip across a little gap of air, you have felt that soft rubbery push when you bring two of them together the wrong way. That little push, that gentle tug, that is a magnetic field of a strength we would call, a fraction of what we get here on the Earth itself, and the Earth's own field is so mild that a compass needle needs to be balanced on a near frictionless pin before it will bother to swing around and point north. That is our everyday acquaintance with magnetism. Gentle, polite, easily ignored. Take that gentle thing and multiply it. An ordinary neutron star, nothing special, just a run-of-the-mill member of the family, carries a magnetic field somewhere between 100 million and 1 trillion times stronger than anything you would find at the surface of the Earth. I want you to feel how empty those words are until you push on them. 1 trillion times. Not 1 trillion times stronger than your icebox magnet. 1 trillion times stronger than the whole planet's field. The field that stretches out past the moon and wraps the entire Earth in an invisible shell. Squeeze all of that, and much more, into a ball you could drive across in 20 minutes. And then, because nature is never content to stop at merely unimaginable, there is a special breed of these stars we call the magnetars. These are the show-offs of the family. Their fields run up to something like 1 quadrillion times the strength of the Earth's. 1 quadrillion. 1,000 trillion. I could keep stacking the words, million, billion, trillion, quadrillion, but the words stop meaning anything past a certain point, and honestly, they stop meaning much several steps back. So let me try to make it physical instead. If a magnetar the strength of these strongest ones was sitting where the moon sits, a comfortable distance off, far enough that you would think you were safe, its field would be strong enough to reach across all that empty space and start rearranging the atoms in your body. It would wipe the magnetic stripe off every card in your wallet, though of course by then you would have larger concerns than your wallet. Get much closer, and the field does not merely tug at things. It changes the shape of the atoms themselves. It squeezes the little clouds of electrons that make up every atom in your body, stretches them thin like cigars pointing along the field lines, so that ordinary chemistry, the chemistry that lets your blood carry oxygen and your nerves carry a thought, simply stops working the way it must for you to go on being alive. You would not be crushed, and you would not be burned. You would be unatoned, quietly, at a distance, by nothing you could see or touch, just by the sheer intensity of an invisible field. So look at what you have fallen toward, now that we have added this last layer. Not just a mountain of gravity, not just a spinning top gone berserk, but a thing draped in a magnetic field so violent that it dictates terms to the very electrons in matter, that funnels charged particles along its poles into beams and flings them out across the galaxy, that makes the space around it a place where the rules you grew up with quietly excuse themselves and leave the room. And all of this, the gravity, the spin, the field, the heat, all of it is packed into that same little sphere the size of a town, sitting out there in the dark, having said nothing, having asked nothing of the universe, simply being what the death of a great star leaves behind. And here is what I keep coming back to, lying awake with it. Every single one of these outrageous properties we did not guess in a fever dream. We reasoned our way to them, or we caught the faint edge of them in a machine, the way that student caught the scruff on the paper. Somebody worked out that a ball of neutrons could hold together. Somebody measured a ticking too regular to be a coincidence. Somebody timed the beam and found the spin. Somebody watched the light from the surface and read the temperature and the pull right out of the color of the glow. Piece by patient piece, the whole impossible portrait got assembled, not by anyone who ever went there, because nobody could ever go there and come back, but by people sitting quietly on this ordinary planet, holding a pencil, refusing to look away from the smudge. And there is one more thing these stars can do, the strangest and the most beautiful of all, which happens only when two of them find each other in the dark. Picture it slowly, because it deserves to be pictured slowly. Two of these dead cities of neutrons, each one heavier than the sun and yet no wider than a town, are circling each other. They did not start out close. Long ago they were two ordinary giant stars, each one perhaps 10 or 15 or 20 times the mass of the sun, and each of them burned bright, and each of them died in its own supernova, and each of them left behind one of these dense little cinders. And by some accident of birth the two cinders were bound to one another, held in a slow gravitational waltz, turning around a common center the way two dancers turn holding each other at arm's length. For a long time, and I mean a truly enormous time, millions of years, hundreds of millions of years, they just turn. Nothing seems to happen. If you glanced at them, you would swear they were stable, permanent, going around and around forever. But they are not going around forever, and here is the quiet catastrophe hidden inside the picture. Whenever a mass is accelerated, it stirs the fabric of space itself, and two masses swinging around each other are being accelerated the whole time, constantly, every instant of the turn. So they send out ripples, ripples in space. Not ripples in some medium sitting inside space, but ripples in the shape of space, in the very distances between things. These are what we call gravitational waves, and for most of a century they were only a line in an equation. A whisper Einstein wrote down and half doubted, a thing so faint that most sensible people assumed we would never in 1,000 years actually feel one pass by. A gravitational wave rolling through your body stretches you one way and squeezes you the other, but by an amount so absurdly tiny that the word tiny is an insult to how small it is. We are talking about a change in length far, far smaller than the width of a single proton spread across a machine miles long. And yet we built the machine anyway. While we get to that machine, stay with the two stars, because their story is not finished. Every ripple they send out carries away a little energy. And energy is not free. The only place that energy can come from is the orbit itself. So each ripple, each little shudder of space they send off into the dark, costs them a sliver of their motion, and the orbit shrinks. Just a hair. Then another hair. For eons the shrinking is so gentle you could never notice. But shrinking has a wicked habit near these objects. The closer the two stars get, the faster they must swing to hold a tighter orbit. The faster they swing, the harder they whip space around them. The harder they whip space, the more powerful the waves. The more powerful the waves, the more energy pours out. And the more energy pours out, the faster the orbit shrinks. Do you feel the trap closing? It is the same runaway we have met again and again on this long night, the same thing that made the tides bite so suddenly at the end. What began as a lazy waltz over hundreds of millions of years becomes, in its final minutes, a shrieking blur. In the last seconds before the end, those two cities are whirling around each other hundreds of times every second, sweeping through space faster and faster, screaming out gravitational waves at a pitch that literally rises. An upward slide higher and higher, the way a whistle climbs as it comes toward you. Physicists have a homely little name for that rising slide. They call it the chirp, and it is a good name, because if you take the pattern of the wave and turn it into a sound you can hear, that is exactly what it does. It goes woo, and it climbs faster and faster, up and up, and then it stops. The chirp of two stars falling into each other's arms and never letting go. On one particular morning we heard one. On the 17th of August, in the year 2017, the ripples from one of these mergers finally reached the Earth. They had been traveling for something like 130 million years, crossing a gulf so wide the number stops meaning anything, coming from the direction of a galaxy called NGC 4993. And they washed over our little planet, and they stretched every one of us by less than the width of a proton, and almost nothing on Earth felt it. But two enormous instruments felt it. They had been waiting, patiently, arms held out across miles of vacuum, listening for exactly this shudder, and the shudder came, and the machines wrote down the chirp. That signal has a name now. We call it GW17817. And it was the first time in the whole history of our species that we heard two neutron stars die together. Here is the part that lifts the hair on my arm, and I hope it lifts yours, gently, as you lie there. Hearing the chirp was only half of what happened that day, because these were not black holes which swallow everything and show you nothing. These were neutron stars, made of actual stuff, actual matter, that iron crust and that ocean of neutrons and whatever strange thing hides in the core. And when two balls of that stuff smash into each other at a good fraction of the speed of light, they do not vanish quietly. They erupt. They fling a spray of neutron-rich matter out into space, a hot, violent cloud, and in that cloud something happens that has haunted chemists and astronomers for generations. So not only did our instruments feel the ripple in space, but telescopes all around the world swung to that same patch of sky and saw a new point of light appear, a glow that had not been there the night before, brightening and then fading over days. For the very first time, we had caught a single event in both channels at once, in the trembling of space and in ordinary light. We had felt it and we had seen it, together, the same thing, two entirely different senses agreeing on one dying pair of stars. People had dreamed of that for decades and mostly assumed it would slip past them. It did not slip past. It arrived. And now let me tell you what was in that fading glow, because this is where the whole long night turns around and points straight back at you. Think about where the ordinary elements come from. The lightest ones, the hydrogen and the helium, are nearly as old as the universe. The middleweight ones, the carbon in your pencil, the oxygen you are breathing, the calcium in your bones, the iron in your blood, those were cooked in the hearts of ordinary stars and scattered by ordinary supernovae. We have understood that story for a long while, and it is a lovely story. But it has a gap in it. There are heavy elements, the really heavy ones, that an ordinary star simply cannot make in the usual patient way, because building them means jamming neutron after neutron onto a nucleus faster than the nucleus can fall apart, and you need a place drowning in free neutrons, a place unimaginably rich and hot and quick to do it. For years we pointed at the sky and said, those heavy atoms must be made somewhere, but we were not entirely sure where. The glow from that collision answered us. In the light of that kilonova, that is the name for the afterglow when two neutron stars merge, we read the fingerprints of exactly that kind of frantic neutron jamming, the process that builds the heaviest elements by brute force in a fraction of a second. And among the things it builds are the ones people have killed for and crossed oceans for and worn on their fingers. Gold. Platinum, made not in some gentle furnace, but in the wreckage of two dead cities colliding after waltzing for 100 million years, in a spray of matter flung across space, cooling as it flies, freezing into atoms of the most precious metals we know. So let that settle over you as the night goes on. The gold in a wedding ring did not come from the ground, not really. The ground only kept it. It came from the sky long before there was a ground, from a catastrophe like the one we finally heard on that August morning, from two objects exactly like the one we have been imagining ourselves falling into all this time. The very same thing that would shred a human body at 190 kilometers out, that would smash it into a crust 10 billion times stronger than steel, that would blaze with a light bent halfway around itself, that same monstrous impossible object, when it embraces another of its kind, becomes the forge for the loveliest and gentlest ornaments we own. The destroyer and the jeweler are the same star. I find I cannot let that go once I have picked it up, and I do not think you will either. We started tonight with the plainest question there is, the question a child asks, what happens when a thing falls? And we followed the falling, patiently, one layer at a time, all the way down into a place where matter forgets how to be matter, where gravity forgets how to be gentle, where light forgets which way is out. And now, at the far end of the falling, we have arrived at the thing on your own hand. There is more still to say about how all of this hangs together, and about one last question I have been quietly saving, the one about whether any of it could ever truly be survived, and we will get there before the night is out. So let me pick that thread up gently, the one I said I was saving. Could you survive it? Could anything? And I want to be honest with you the way a friend is honest at the end of a long night, not the way a brochure is honest. The answer, when you fall toward one of these things as a body made of ordinary flesh and ordinary bone, is no. Not almost no. Not no with an asterisk. Just no. And I want to walk you through why the no is so complete. Because the completeness of it is itself a kind of teaching. Think back to that rope we talked about, the one with a strength of 10,000 newtons, snapping cleanly at a distance of about 190 kilometers from the center of a star only 12 kilometers across. Now, a rope is a simple thing. It is one long fiber with a single job to resist a pull along its length. You are not a rope. You are a crowd. You are a city of little ropes all tied together at strange angles, tendons and blood vessels, and the fine threads that hold one cell against the next, and every one of them has its own snapping point, and every one of them is weaker than a good climbing rope. So the failure does not come all at once, like a single note. It comes like an orchestra falling out of tune section by section, the weakest joints letting go first, far out, where the pull between your head and your feet has only just begun to outrun the strength that holds you together. And because the tidal force climbs as one over the distance cubed, each kilometer you fall after that first failure is not a little worse. It is enormously worse. Halve the distance and the stretching grows 8 times. Halve it again 8 times more. The unraveling does not proceed at a steady pace. It accelerates into itself, faster and faster, so that whatever is left of you covers the last stretch toward the surface in a state I do not have a calm enough word for. And notice, please, where all of this happens. 190 kilometers out. The surface, the actual solid ground of the star, is still down at 12 kilometers from the center, more than 150 kilometers below the place where you have already come apart. You never touch it. You never see it up close as a whole person. The star does not let you arrive. It disassembles the messenger long before the message can be delivered. There is something almost fastidious about that, the way it will not permit an intact thing to reach it. Now you might say to me, all right, the body is fragile, I grant you that, but suppose we were clever. Suppose we built a vessel. Suppose we made it out of the strongest stuff we know, and we fell inside it, sheltered. Would the shell save us? And this is a lovely question, because it forces us to think about what strength even means. Remember what I told you about the crust of the star, that it is reckoned to be something like 10 billion times stronger than steel. 10 billion. Hold that number for a moment, because it tells you the scale of what you are up against. The star itself, at its own skin, is built out of material braced against forces we cannot begin to match. Your vessel is made of steel, or something a few times better than steel if you are lucky and rich. It is not made of neutron star crust, because nothing in your world is. And the tidal stretching does not care in the slightest whether the thing being stretched is a person or a ship. It reaches into every object equally, pulling the near end harder than the far end, and it will find the difference between the top of your vessel and the bottom of it, and it will pull them apart with the same ferocious one over distance cubed impatience. A stronger hull only means you come apart a little deeper in, a few kilometers closer, before the same verdict lands. You have not escaped the sentence. You have only paid for a slightly longer fall, and I have not even let the other executioners into the room yet. We spoke of the magnetic field, and I want you to feel how strange a killer that is, because it does not touch you and it does not need to. An ordinary neutron star carries a field somewhere between 100 million and a trillion times stronger than the gentle one that turns a compass needle here at home. And the fierce cousins, the magnetars, carry fields reaching toward a quadrillion times the strength of Earth's. A quadrillion. Now, a field that strong is not merely a force that tugs on iron. It reaches down into the very shapes of the atoms in your body. It squeezes the clouds of electrons that give every atom its width, stretching them thin and long, so that the atoms themselves are no longer little spheres but little needles, and a needle-shaped atom does not do the chemistry that a round one does. The chemistry of life simply stops working. You would be undone, in that region, not by a blow, but by the quiet withdrawal of the rules that let matter behave like matter. And here is the part I find almost unbearable in its beauty. You would be dead of the magnetism long before you were close enough to be torn by the tides. The star has more than one way to end you, and they do not wait their turn politely. They arrive together. So no, there is no shell, no cleverness, no material in the human world that reaches that place and comes back. And I do not say this to sadden you at the end of a long evening. I say it because I think the impossibility is one of the most honest things physics has to offer. We spend so much of our lives being told that with enough determination anything can be done. And then the universe sets down, quietly, in a corner of the sky 6,500 light years away, or 18,000 or 28,000, depending on which one you pick, an object that says gently, no, not this, not ever, not you. And it is not being cruel. It is only being itself. The very same properties that forbid you also make it one of the most extraordinary things that exists. But I do not want to leave you standing at a locked door, because that is not really where the physics leaves us. Here is the turn. You cannot go there. But something did go there, once, a long time ago, and that something is you. Let me explain what I mean, because it is not a trick. Every neutron star we have talked about tonight began as the core of a great star, a star of perhaps 10 to 25 times the mass of our sun, that lived its bright life fusing lighter things into heavier things, hydrogen into helium, helium into carbon and oxygen, on, building an onion of ever heavier ash, until it reached iron and could go no further, because iron is the ember that will not burn. And when that iron heart grew too heavy, past the limit that a sea of electrons can hold up, it fell. It fell in less time than it takes you to draw a breath, collapsing from something the size of our Earth down to something the size of a city. And in that fall, the protons and the electrons were crushed together into neutrons, and the neutron star was born in a flash of light we call a supernova, a single dying star briefly outshining 100 billion living ones. Now hold that picture beside the other one we ended on, two of these dead cities of matter, circling each other for ages, spiraling closer and closer, until they touch and merge and fling out a spray of newly forged heavy elements, gold and platinum and more, scattered into the dark. That is not a fable. We watched it happen, in gravitational waves and in light together, on the 17th of August, 2017, in a galaxy called NGC 4993, more than 130 million light years away. The gold was made there. And the gold has to go somewhere. It drifts for ages through the thin gas between the stars, and it settles into the clouds that collapse to make new suns and new worlds, and some of it, a little of it, ends up in the crust of a small warm planet, and some of that ends up dug from the ground and pressed into a ring on a finger. So the thing you cannot fall into is the thing that made the metal on your own hand. You were spared the fall, but the atoms were not. The heavy elements in your blood, the iron that carries the very oxygen keeping you alive as you drift towards sleep, that iron was forged in the hearts of stars that died to make things like the one we have been falling toward all night. You are, in the most literal accounting, the ash of that fire, walking around, warm, curious, asking what happens when a thing falls. You could not survive the neutron star. But in a sense that is not sentimental, it is only true. You already came through it long ago, and here you are. There is one more piece I have been circling about time itself down there, about how the very seconds stretch as thin as the atoms do, and I think that is where I would like to bring us to rest before the night finishes. Because it turns out the strangest thing that happens to you near that star is not to your body at all. Let me tell you what I mean by that, because it is easy to say the seconds stretch and it sounds like a poet talking. But it is not poetry. It is the plainest kind of physics, and it follows from something you already believe, if you sit with it a moment. Time does not run at the same speed everywhere, it runs slower where gravity is stronger. Down in a deep well of gravity, a clock ticks lazily. Up high, far away, a clock ticks briskly. And near a neutron star, the well is so deep that the difference stops being a curiosity you measure with fussy instruments and becomes a thing you could almost feel, if feeling were still on the menu for you at that point. Picture two clocks. One you keep with you, falling. The other you left behind with a friend, safe, a long way off, watching through a telescope, sipping something warm. On Earth we have this same effect, but it is so tiny it takes the most delicate atomic clock to catch it. Lift a clock up a single flight of stairs, and it runs a hair faster than the clock in the basement, because it sits a little higher out of the Earth's gravity well. The difference is fantastically small. You would never notice it in 100 lifetimes. But it is real, and it has been measured, and once you accept that it is real at the scale of a staircase, you have to accept what it becomes at the scale of a city-sized ball with the mass of a star and a half. Near that star, the slowing of time is not a hair, it is enormous. Remember that number we kept coming back to, the compactness, the ratio of the star's own gravitational radius to its actual radius. For a neutron star, that ratio sits somewhere between about 2/10 and 1/2. That is not a small fraction hiding in a decimal place. That is a serious slice of the way to a black hole, and the amount by which time slows, the amount by which the light crawls out redder and wearier than it went in, depends on exactly that ratio. There is a clean little relation for it, and I will say it in words so it does not frighten anyone half asleep. The temperature you see from far away, the glow that finally reaches your distant friend's telescope, equals the temperature right at the surface multiplied by the square root of 1 minus that compactness ratio. Now think about what the square root of 1 minus a number does. If the ratio was 0, if there were no gravity to speak of, you would multiply by the square root of 1, which is just 1, and nothing would change. The light would arrive exactly as it left. But push that ratio up toward 1/2, and now you are taking the square root of 1/2, which is about 7/10. So the light limps out at 7/10 of the temperature it truly had. The star is genuinely hotter than it looks. Its color is a lie told by gravity, and time, for anything sitting down there, is running at that same 7/10, dragging behind the clocks of the wider universe. That is the surface. Falling in, on the final approach, you go deeper still, and the effect only sharpens. To your friend far away, watching you fall, the last stretch of your descent seems to take longer and longer. Not because you are slowing down. You are not slowing down. You are, if anything, screaming inward faster than half the speed of light. But the light carrying the news of you back out to your friend has to climb out of that deepening well, and each photon climbs out a little more tired, a little redder, a little later than the one before it. So your friend sees your fall smeared out, stretched thin in time the way your body is about to be stretched thin in space. The picture of you reddens. It dims. It seems to hesitate. And a strange gentleness enters the scene, because from the outside it never quite looks finished. But here is the part I find genuinely lovely, and it is the reason I wanted to save it for the quiet end of the night. For you, falling, none of this feels slow. Your own clock, the one you carry, the beating of whatever is left of you, feels perfectly ordinary right up until the tides tear the ordinary away. You do not experience your own time as sluggish. Nobody ever does. Time always feels normal from the inside. It is only when you compare your clock to somebody else's, somebody standing in a shallower part of the well, that the disagreement appears. The two of you would come back together, if such a reunion were possible, and simply disagree about how much time had passed. Not a matter of opinion, not a trick of perception, a real, measured, physical disagreement about the number of seconds that went by. That is the thing that is hard to put down once you have picked it up. There is no single master clock ticking away over the whole universe, keeping everybody honest. Every clock only ever tells its own local truth, and gravity is what makes those truths drift apart. We are so used to thinking of time as the one thing that cannot be pushed around. Space we can imagine bending. You can bend a wire, you can warp a sheet of rubber, you can picture the fabric sagging under a heavy ball. But time feels sacred, untouchable, the steady drummer at the back of the room keeping the beat no matter what the band does. And the neutron star says, no, the drummer slows down too, right along with everything else, when you carry him down into the deep. The beat itself sags under the weight. That is what I meant when I said the strangest thing that happens to you near that star is not to your body at all. Your body is destroyed by a force you can write down in a single line, the difference in pull from your head to your feet, growing as one over the distance cubed. That is violence, but it is familiar violence. It is just pulling, harder and harder. The stretching of time is a different order of strange, because it touches the stage the whole play is performed on and not merely the actors. And you already live inside a mild version of it every day, without a thought. Your head, right now, is aging very slightly faster than your feet, because your head is a little farther from the center of the earth and sits a little higher out of the well. Over a whole lifetime, the difference amounts to less than the blink of an eye, far too small to matter to anything you would ever care about. But it is not zero. It is the same effect, the very same physics, just turned down to a whisper. Near the neutron star, that whisper becomes a roar. The gap between your head's time and your feet's time, which on Earth is a laughable nothing, would down there be one more way the star pulls you apart. Even the flow of time would not be the same at your two ends. So let us sit with the picture as it truly stands, now that we have climbed all these layers, one at a time, the way I promised at the very beginning when all we had was a ball dropped from a hand. We started with the plainest thing in the world, an object falling, and we asked only what falling really is. And falling, it turns out, was never simple. It was gravity, and gravity was never just a force pulling things down. It was the shape of space, and it was the pace of time, and the deeper the well, the more both of them bend, until at a certain unimaginable depth, the bending of space rips you into a spray of atoms, and the bending of time makes the whole event look, from far away, like it is happening in a slower and slower and ever-reddening dream. The tides get the body, that we have said, and said carefully, with the rope snapping out at about 190 kilometers from the center, while the hard surface waits far below at only about 12. You are undone long before you arrive. But suppose, just as a thought to hold, that you could somehow ride down intact, that no tide could touch you. Even then, the star would take your time. It would peel the seconds off you, one register slower than the seconds of the world you left, and it would hand your last moments to the distant watches stretched and dimmed into a long red hush. There is no armor against that. You can imagine a suit strong enough to resist crushing. You cannot imagine a suit that makes your clock agree with a clock 1,000 kilometers up. The disagreement is not about you. It is about where you are standing in the geometry of the thing. I want to turn us now, before the night is through, back toward the wider sky, because a neutron star is not only a place where a falling thing meets its end. It is also, out there, spinning, a lighthouse, a forge, a bell that was struck once in a supernova and has been ringing ever since. We have spent our hours falling in. Let us spend a little while climbing back out and looking at these objects the way the people who first found them had to look, from very far away, with almost nothing to go on but a faint and stubborn tick arriving out of the dark, exactly on time, again and again, refusing to be explained. Picture the two young men who first dared to say such a thing could exist. It was 1933, and a supernova had just been understood as a real explosion of a real star, and two astronomers, Walter Baade and Fritz Zwicky, sat down and made a leap that ought to have gotten them laughed out of the room. They said, suppose a star runs out of fuel and its core caves in. Suppose it caves in so hard that the protons and the electrons are pressed together into neutrons and the whole core becomes one gigantic ball of neutrons packed like a nucleus. They wrote it down. A star made of neutrons. And then, for more than 30 years, nothing. No one saw one. No one could see one. It was an idea sitting in a drawer, too strange to prove, too clean to throw away. That is a wonderful kind of patience, to propose something and then wait, not knowing if the sky will ever agree with you. So let us go to the moment the sky finally answered, because it did not answer through some grand telescope aimed by a famous man. It answered through a graduate student out in a field, tending to an instrument she had helped build with her own hands. Her name was Jocelyn Bell, and the instrument was not the polished dome you picture when you think of astronomy. It was acres of posts and wires strung across the English countryside, a great clumsy net for catching radio waves. She had helped hammer it together, and now she was the one reading the output, which came not on a screen, but as ink scratched onto long rolls of paper by a pen that twitched with every wobble of the signal. Miles and miles of paper. She read it by eye. She learned the personality of that chart the way you learn the sound of your own house at night, which creaks are ordinary and which one is a footstep that should not be there. And one day, late in November of 1967, on the 28th to be exact, she found a footstep that should not have been there. A little bit of scruff, she called it. A smudge of signal that did not behave like the whistle of a passing spacecraft, and did not behave like the crackle of a storm, and did not behave like the interference of some machine down the road. It kept coming back. And when she looked closely at that smudge, she found something that genuinely frightened the people who first saw it. The signal was ticking. Not roughly, not approximately. It was ticking with a regularity you would expect from the finest clock ever made. Once every 1.3373 seconds, a pulse. And then again. And then again. Precise past belief. Now put yourself in her shoes for a moment, because this is one of the most human moments in all of science. You have a signal from the sky that is beating like a metronome. What in nature beats like a metronome? Nothing you know of. Stars flicker, they flare, they pulse slowly and sloppily, but they do not tick like a pocket watch. The only things you have ever encountered that keep time that cleanly are things that somebody built, things with intention behind them. And so, half as a joke and half in genuine unease, the signal got a nickname. They called it LGM1. Little Green Men, number 1. Because if you cannot rule out that a civilization is sending you a beacon, you had at least better write down the possibility, even if you write it down with a nervous laugh. But here is the thing I admire most about how she handled it. She did not fall in love with the romantic answer. A beacon from another world, imagine the glory of finding that. It would be the story of the century, and yet she kept her head. She reasoned that if this were truly some civilization signaling, it would be an extraordinary coincidence for their planet to be sitting still relative to hers, and their signal ought to show the fingerprint of a world going around its own sun. And then, while she was still chewing on that, she found a second one, a different tick in a different part of the sky coming from a completely different direction, and that settled it in her mind almost at once. Two separate civilizations on two separate worlds, both aiming a beacon at one graduate student in England, both discovered in the same few weeks? No, that is too much to swallow. Whatever this was, it was natural. It was a thing the universe does. It just happened to do it with a precision nobody had thought the universe capable of. And what was it? It was exactly the thing Bade and Zwicky had scribbled down 34 years before, and no one could confirm. A neutron star. But now spinning, spinning fast, and beaming radio waves out along its magnetic poles like a lighthouse throws a beam out along the water. Every time that beam sweeps across the earth, you get a tick. The clock is not really a clock at all. It is a searchlight on a spinning ball, and you happen to be standing where the light passes. The regularity you are hearing is nothing more mysterious and nothing less astonishing than the steadiness of a thing turning in empty space with nothing to slow it down. A neutron star is the best flywheel in the universe. It is small, it is unspeakably heavy, and there is no air to drag on it and no ground to grind against. Once it is spinning, it just keeps spinning, and it keeps time better than any craftsman ever could. Now I want you to hold on to that image. The lighthouse, the sweeping beam, the tick arriving out of the dark exactly on schedule, because it changes how you should feel about the whole grim business we spent the night on. We fell into one of these things and we were shredded, and we struck a crust harder than any steel, and we saw our own light bent back at us in a red hush. All of that is true. But from far away, that same object is not a monster at all. It is a timekeeper. It is one of the most dependable, most beautiful, most patient objects that exists. Sailors used to steer by lighthouses. There is a real sense in which we can steer by these. Astronomers have used the ticking of certain neutron stars, the ones that spin hundreds of times a second and hold their rhythm across years, as clocks scattered across the galaxy. You can watch for the faintest stumble in their beat and learn things about the space the signal traveled through to reach you. The very steadiness that fooled people into whispering about little green men turned out to be a gift, a set of natural clocks hung up all across the sky, ticking away, free for anyone patient enough to listen. And think about what that steadiness is really made of. When Belle read that ink on the paper, she was reading the rotation of a ball the size of a city, a ball with more mass than our sun, turning once every 1 1/3 seconds. Every tick was a whole city-sized nucleus completing part of a turn. The pen twitched, and the twitch was the far side of a dead star swinging around to face her. There is something almost unbearable in that when you sit with it. A pen and some ink and a roll of paper in a damp English field, faithfully drawing the spin of an object so dense that a spoonful of it would outweigh a mountain, an object nobody had ever seen and many had stopped believing in. The largest thing and the smallest thing, the collapsed heart of a giant star and the trembling of a cheap pen, meeting on a strip of paper because a young woman was paying attention and refused to dismiss the scruff. That is the part I never want you to lose as you drift off. The universe did not announce these things with trumpets. It announced them with a whisper so faint and so regular that the honest first guess was a mistake, a machine, a hoax, a signal from someone else. It took a certain kind of stubbornness to say, "No, let me look again, let me be sure, let me not fool myself with the answer I would most love to be true." She did the hardest thing in science, which is to talk yourself out of the exciting explanation and keep digging until you reach the true one. And the true one, in the end, was far stranger than little green men. It was a corpse of a star, spun up in its own death, sweeping a blade of radio light across the whole galaxy and keeping better time than anything human hands have ever made. The little green men were a fiction. The lighthouse made of crushed atoms, turning in the dark, ringing out its rhythm for anyone who would listen, that was real, and it had been out there the whole time, waiting for someone to write it down. Think for a moment about what that means. That a thing keeping better time than any clock in any laboratory was doing so, not because anyone wound it, not because anyone tuned it, but simply because it was heavy and small and spinning and had nowhere to put its motion. A skater pulls her arms in and speeds up. That is all this is, taken to an absurd extreme. A great bloated star, wider across than the orbit of a planet, pulls its arms in during the last second of its life, collapses to the size of a town, and spins up until it is turning tens or hundreds of times every second. The steadiness we hear is just the steadiness of a top that has almost nothing to slow it down. Out there in the near vacuum, with no air to drag on it, no ground to rub against, the only thing stealing its spin is the faint radio whisper it throws off, and a trickle from its own magnetic field. So it coasts, and it coasts, and it keeps the beat for 1,000 years, 10,000 years longer, the most patient metronome in creation. Now let me carry you one step further out, because so far I have kept you and your falling body all alone with a single star. One object, one victim, one long plunge. But nature is rarely so tidy. Stars very often come in pairs. They are born together out of the same collapsing cloud, and they spend their whole lives circling one another, two dancers holding hands and turning about a common center. And when both of those dances are massive enough, both of them can end in the same violent way, each collapsing its iron heart, each leaving behind one of these small, heavy corpses. So now you have two neutron stars, two cities of crushed matter, still holding hands, still turning about each other in the dark. Here is the thing about that dance. It cannot last forever. Two masses whirling around each other stir the very fabric they sit in. They make ripples. Not ripples in water, not ripples in air, but ripples in space itself, in the shape of distance, in the geometry of the room. We call them gravitational waves, and for a long time they were only a prediction, only ink on paper, a consequence of the equations that no one had ever caught in the act. Every time these two stars swing around, they shed a little of their energy into those ripples, and the ripples run off across the universe at the speed of light. And because they are losing energy, the two stars must fall a little closer together. And when they fall closer, they swing around faster. And when they swing faster, they make stronger ripples and lose energy quicker still and fall closer yet. Do you feel the trap closing? It is the same runaway we mapped before, the same cruel arithmetic where getting closer makes everything worse, only now it is playing out over millions of years instead of milliseconds. Two stars that might have circled each other calmly for an age begin, at the very end, to spiral inward faster and faster. A whirlpool tightening on itself, the two of them screaming around each other hundreds of times a second in the final breath before they touch. And then they touch. Two objects, each heavier than our sun, each the strength of the thing you fell toward, each with a crust 10 billion times stronger than steel, slammed together at a good fraction of the speed of light. There is no gentle word for what happens then. It is the most violent event the modern universe knows how to make short of building a black hole outright, and often it builds one of those too, in the same instant. But before the darkness closes over it, something extraordinary is flung outward. Remember what these stars are made of. They are made of neutrons, packed together tighter than anything else that still counts as ordinary matter, a whole city's worth of neutrons with no room to breathe. When the two stars smash and shatter, a spray of that neutron-rich material is thrown off into space, no longer held down by the crushing gravity, suddenly free. And free neutrons, loose in the wreckage, do something marvelous. They rain onto whatever atomic nuclei are nearby, and those nuclei drink them in, one neutron after another, swelling up, growing heavy, becoming kinds of atoms that the calm interior of an ordinary star could never patiently build. This is the process by which the heaviest elements are made, and it needs exactly this: a sudden flood of neutrons in a place gone mad with violence. In the glowing debris of two neutron stars tearing each other apart, the periodic table fills in at its heavy end. Gold is made there. Platinum is made there. The heavy, precious, stubborn atoms that we dig out of the ground and press into rings and wires, forged not in any furnace on Earth, but in the collision of two dead stars, long ago, somewhere else, and scattered outward to drift for ages before they ever became part of a planet. I want you to sit with that for a moment, quietly. The way you might sit with a thought just before sleep. The gold in a wedding band was not made on Earth. It could not have been. The Earth has never had and will never have the conditions to make it. Every atom of it was cooked in a catastrophe out among the stars, in the shredding collision of two objects exactly like the one I have been dropping you into for these last hours, and then it wandered, cold and dark, through the emptiness, until it fell into the cloud that became our sun and our world, and settled into the crust and waited to be found. You have been carrying a piece of a neutron star collision on your finger, or in your teeth, or in the wiring of the machines around you, and you never knew it. For the longest time, this was a beautiful story we could only tell, not show. We believed it must be roughly true, because we could not think where else the heavy elements would come from in the amounts we see. But belief is not the same as catching nature red-handed. And then, one day, we caught her. Detectors built to feel those ripples in space, instruments so sensitive they can notice the length of a long tunnel changing by less than the width of a single proton, felt a tremor pass through the Earth. It rose in pitch over less than a minute, a rising note, a chirp, exactly the sound the equations said two neutron stars should make as they spiraled into their final embrace. And then, seconds later, telescopes swung to the same patch of sky and saw a new point of light kindle in a distant galaxy. A fresh glow that had not been there the night before, brightening and then fading over days in just the way you would expect if a cloud of freshly forged heavy elements were cooling in the wreckage. For the first time in the whole history of our species, we had felt an event with the tremor of space and seen it with light. Both at once, the same collision announced in two completely different languages, and the two accounts agreed. We were no longer only listening to the shiver of the ground or only reading the color of a far-off spark. We had both, and they told one story, and the story was this. Two neutron stars, out in another galaxy, an enormous distance away, so far that the light we finally caught had been traveling toward us since long before there were any people to catch it, had wound down their long dance, fallen together, and in dying had scattered a fortune of gold and heavy metal into the dark. We did not deduce it. We did not merely calculate it. We were there, in the only way a creature bound to one small planet can be there. We felt it arrive. So let me fold this back into the long fall I promised you at the very beginning. The one that started with nothing more than a ball slipping out of a hand. Everything I have shown you about the single star, the runaway pull, the tides that grow as one over the distance cubed, the rope that parts far out in empty space, the crust harder than any steel, the light that bends back to show you more of a surface than should be possible, the neutron ocean and the mystery at the core, all of it is not only a thing that could happen to you if you were unlucky enough to fall. It is a thing that has happened, over and over, to whole stars falling into one another, since long before our world was made. The very violence I have been describing as your doom is the same violence that made the ground you stand on rich, that salted the young earth with the heavy atoms that would one day sit in your blood and your bones and your buried treasure. You began this fall as a single body dropped toward a single star. I want to leave you, before we are quite finished, holding the larger picture, because there is one more turn to take. We have talked about falling in. We have not yet asked what it would truly mean to stand at a safe distance and watch one of these things turn, and time itself run slow near its surface, and the whole notion of when and how fast begin to bend the way the light bends. That is where I would like to take you next. Gently, while the metronome of that far-off corpse keeps ticking in the back of your mind, steady as it has been for 10,000 years, steady as it will be for 10,000 more. So come away with me now. Let us stop falling for a while. Let us imagine we have a ship, a good sturdy one, and we park it far enough out that the tides are gentle and the pull, while enormous, is something our engines can hold us against. From here, the star is a small bright bead, no bigger to the eye than a coin held at arm's length. And yet it is turning, and you can feel in your bones that something is wrong with the way it turns. It is too smooth. It is too certain. It keeps a beat the way nothing in ordinary life keeps a beat. Not a heart, not a clock, not the tapping of a foot. It simply ticks and ticks and ticks, and the ticking has not wavered by any amount you could measure since long before there were ships or eyes or anyone to be troubled by it. Now I want to tell you something strange about watching a clock that sits deep in a well of gravity. And this is not a trick of the eye, and it is not a story I am inventing to keep you awake. It is one of the truest things we know. Time near a heavy body does not run at the same rate as time far from it. Down close to that surface, where the pull is 200 billion times what you feel in your chair, the seconds themselves stretch out. They grow long and slow, like honey pouring on a cold morning. If you could set a clock on the surface of that star and somehow keep it from being crushed and read it from your safe perch far away, you would see it lagging behind your own. Its seconds would arrive late. Its minutes would drag. And the light climbing up to you from that surface, the light carrying the picture of whatever is down there, would climb out tired, drained of its energy, its color pulled toward the red the way I described to you a while ago. This is the same effect. The slowing of the clock and the reddening of the light are two faces of one fact. Deep in the well, time is cheap and long. High up where we float, time is quick and dear. So picture what this does to the beat. The star spins, let us say, 30 times in a second, the way the heart of the old crab does, the one that has been turning since the sky lit up over the astronomers of the year 1054. 30 times a second, down there on the surface. But you, floating far away, you do not receive 30 ticks a second quite the way they were sent. The light climbing out of the well carries the rhythm to you slightly stretched, slightly slowed, the message aged by its long climb against the pull. It is a small effect at your safe distance, but it is real, and if you fell closer it would grow, and the closer you fell the more the whole tune would sag and deepen, like a song played on a phonograph you are slowing with your thumb. The dying man's watch, seen from the mountaintop, runs slow. And here is the part that unsettles people the first time they meet it. To the man himself, nothing is wrong. His seconds feel exactly 1 second long. His heart beats at its ordinary pace. He does not feel time crawling. It is only from the outside, only from up high, that his whole life looks slowed. Time does not announce its own stretching. You cannot feel your own seconds growing heavy. You can only see it in someone else, down deeper than you are. Let me make this a little more vivid, because I think it is one of the loveliest and most disturbing ideas in all of physics, and it deserves to be turned over slowly in the dark. Suppose two of us go on this expedition, you and I, and suppose you are braver than I am, or more foolish, and you take a small craft and drop toward the star while I stay behind, holding station far out, watching you through a good telescope. As you fall, I keep my eye on the little clock face painted on the back of your ship, and on the lamp you have promised to blink at me once every second by your own reckoning. At first the blinks come to me once a second, near enough. But as you sink into the well, the blinks begin to space out. Once a second becomes once every second and a bit. Then every 2 seconds. Then slower still. Your voice on the radio, if you were speaking, would drop in pitch, growing deep and drawn out, the words spreading like syrup. And to you, inside that ship, nothing has changed at all. You feel fine. Your clock ticks normally. You blink your lamp once a second briskly, wondering why I have gone so quiet. From your side, it is I who have sped up. My blinks come to you faster and faster. My voice climbs higher and thinner. Each of us thinks the other has fallen out of step, and each of us is right, because there is no single master clock hung up in the sky over the universe to settle the argument. There is only your time and my time, and the honest difference between where we stand in the pull of that terrible little star. Now, of course, long before your blinks would slow to a true crawl, the tides I warned you about would have finished you, and the ship and the lamp and every atom of the message. So this is a thing we can only carry to its full extreme in imagination, or by using a body tougher than any body. A beam of light, a stream of particles, something that does not care about being torn. But the effect is not imaginary. We have measured the tired reddened light climbing out of these wells. We have watched the beats of pulsars and folded in exactly this slowing to make the numbers come right. The stretching of time near heavy matter is not a philosopher's daydream. It is in the arithmetic we use every day to understand what these stars are telling us. And what they are telling us, in that patient, endless ticking, is partly a message about time itself, about how the ground under an idea we thought was solid, this idea of a single universal now, simply dissolves the moment you bring real gravity into the room. Think of what this means for the notion of when. You are used to saying that two things happen at the same moment, and meaning something definite by it. The clock in the kitchen and the clock in the bedroom both say midnight, and you feel that midnight is one thing, shared by both rooms, shared by the whole house, the whole town, the whole sky. And for ordinary purposes it is near enough to true that you never catch it failing. But bring that spinning city of neutrons into the picture and the failure becomes glaring. Midnight on its surface and midnight on your ship are not the same midnight, and they never can be brought into perfect agreement, and the gap between them is not a fault in your instruments. It is built into the shape of space and time around a heavy thing. The heavier and the more compact the thing, the wider the gap yawns. And a neutron star, remember, is about as compact as matter can get before it gives up entirely and becomes a black hole. It sits right at the edge of that cliff. Its radius is only a few times the fatal radius, the one past which even light cannot climb out. So the bending of time around it is not a whisper. It is loud. It is a fifth or more of the way to total, to the place where time as seen from outside would stop altogether at the surface. And that is the quiet horror hiding inside the beauty. If you could pile just a little more mass onto that star, push it past the limit I told you about, the 2 and a fraction suns beyond which the neutrons themselves cannot hold, then the surface would fall inward and keep falling, and the reddening of the light would deepen until the light went out entirely. And the slowing of the clock would deepen until, seen from far away, the clock would seem to freeze forever on its final tick, hanging there, never quite reaching the next second, a last frozen image reddening into darkness and silence. That is the door the neutron star stands just outside of. It is the last thing in the universe made of ordinary touchable stuff, atoms and nuclei and particles you could in principle name, before that door opens and the stuff falls through into a place from which no picture, no beat, no message ever climbs back out. The neutron star is nature holding its breath at the very threshold, refusing, for now, to step over. So when you hear that metronome ticking in your mind, the far-off corpse keeping its steady time, I want you to hear inside it this second, subtler music. Not only is the star turning, the very seconds it hands you are not quite the seconds it keeps for itself. Its now is not your now. Its time is deep and slow and heavy, and yours, out here in the thin gravity where you were lucky enough to be born, is quick and light. Two clocks, two rivers of time, running side by side at different speeds, and no way to ever fully reconcile them. And the astonishing thing, the thing I keep coming back to in the quiet, is that human beings, small soft animals on a warm wet planet, figured this out. We worked out that time bends near heavy things before we had ever seen one of these stars, before we knew for certain they were real. Someone did the arithmetic first, in ink on paper, and only later did the sky confirm it. And how that confirmation came, how we first caught one of these impossible spinning things red-handed, ticking in the dark, mistaken at first for a message from someone else entirely, is a story worth telling slowly. And it begins on a cold night with a young woman and a field full of wires.